All right. Hello. Hello, everyone. Wait, I'm trying to see if this is working. This is, as I mentioned, like my second time. And I hope if you were in the previous stream, you can see that now I have improved a couple of stuff. Did you see that? It's like a little screen, where we put like starting soon. It's great. It's great. So today is the second day. Today is the second day. For anybody that didn't watch yesterday's stream, we are coding a memory allocator from scratch. And yes, if you may be asking, why are we coding a memory allocator? We're doing that for the sake of learning and learning only. So yeah, that's mostly everything. I have dedicated like most of yesterday and of today to figuring out how OBS works, how to set up like, to make the stream remain as a video and like all that stuff. I also created these little scenes. You see, like now I can switch between two things. I can also go to the starting soon screen and so on. it's magnificent. So all right, today I there's also like this little box that displays things in chat. If I type like "Hi everyone," you'll see how it displays in the little box. Oh, that looks terrible. But there you go. I can edit it in real time. That's also great. So, all right. Today we are going to continue on a mission to have a memory allocator from scratch. And for that, I am now able to share my entire screen. So now we can also look at like videos and stuff if we need to learn about red, black trees and all of this stuff that we're going to be working with. And so currently I have open Visual Studio on sort of like where we left, which was precisely creating this red and black tree. So just to allow people to catch up on what we've been doing, yesterday we were working on the design of a memory allocator. Excuse me. The design of a memory allocator. Here I'm also going to create a new window for the memory allocator we had last time. Nalloc. There you go. Sweet. Awesome. I'm going to transfer that to the first workspace. Increase the font a little. There we go. So this was our design for Nalloc last time. We decided that our memory blocks are going to contain this data that we see on screen. Size, the left child, the right child, a parent, and then the color embedded inside the parent thanks to ZM's idea on how to store color in the last two bits of a parent. And basically, the approach we ended up determining was we're going to use a red-black tree in order to find the best fit free block. What that means is, if the user makes a request, like, as I said, like nalloc, I don't know, 12, like allocate 12 bytes for me, what we're going to do is we're going to go through this red-black tree, which in the end is just a binary search tree with extra properties, and we're going to look for the best fit of 12, right? And once we find that, we're just going to return that to the user. So in order to achieve that, of course, we need to get familiar with red and black trees. I didn't really know about red black trees before the day before yesterday, so I haven't really coded one. I understand the concept, but I'm not too familiar with it. So what we're going to do today is we're going to start coding a red black tree. It is, is it as exciting as creating the memory allocator itself? I mean, you will judge it, but it is definitely something that we need to do if we want to get familiar with the concept. So that's exactly what I have on the second workspace. Because yesterday we started creating the red black tree. And today we're just going to continue with that. Right. So what we have written so far, because yesterday we only dedicated like 20 minutes to this. But what we've written so far is the red black tree is sort of, scaffolding of how the class will look like. We will have three methods for now: insert, find, and remove. This find is sort of a find for the best fit, where it finds the ones that greater or equal to, in mathematical terms, the lower bound of whatever is being passed here. And then we have the usual data that you would expect a node to have, right? The left and right children, and then a parent, and the color, data, and a comparator. So now we have to start sort of thinking about what we're going to do. And that brings about a specific situation, and it's the fact that we need to learn about red black trees. So let me transfer this to the second workspace. Oh, shoot. I have you guys here in the... No. Oh. Okay, let me see. There you go. You, please transfer to second workspace. There we go. Perfect. Awesome. And in order to learn about red black trees, I think we can simply go watch maybe a video on red black trees that sort of explains the whole deal. And I'm pretty sure Michael Samble has like very good videos about red black tree. So let's see. Oh, perfect. He has an entire series about it. I remember this.
Check this out. I'm going to show you how I afforded this car.
You got some ads.
Okay, you ready?
Sorry, people.
All right, $118 for car insurance. That's how much I was paying.
We're going to
I picked up the car a few
resist
months ago and
let's see.
Today, we're going to introduce red black trees.
We already sort of know what a red black tree is.
Red black trees are a complicated topic, so I'll use several videos to cover them. In this video, we'll learn about rotations, an important operation when inserting and deleting items from a red black tree. In case you missed my first video, here is a review of red black.
Okay, we have the rules of a red black tree. Then a node is either red or black. That the root and the leaves are always black. That if a node is red, then its children are black. And that all paths from a node to its nil descendants contain the same number of black nodes. Okay, that's
tree
clear
properties.
Enough. I feel it's good if we just write them down here, just to have them as a reference. Some sort of like this. Oh, whoa. Okay. Ostrich. Perfect. So the rules of a red black tree, only known as either black or red. That one is sort of given, so I'm just not going to write it down. But the root and leaves are always black. So, nil. Because we think of the nil as the actual leaves rather than a node that has data in it. We have that if a node is red, its children are black. And then for the third condition, we have that all paths from a node to its nil descendants and then contain or like yeah, sure, contain the same number of black nodes. And for this purpose, I'm gonna squeeze it a little bit. There we go, perfect. So hopefully we can keep the columns within 120 or 100. And this is perfect. All right, we have the rules now. But I'm interested.
Please see my previous video. Let's talk about what you can do with red black trees.
So I'm interested in rotations.
Insert and remove. Inserting and removing items change the structure of the tree and may result in a violation of the red black tree properties we outlined. Rotations alter the structure of a tree by rearranging subtrees. But we said red black trees all are elements of layer 2 rotation using the following tree.
Okay, left rotate.
For now, we won't color the nodes red or black. Instead, we'll color them so it makes the rotation easier to see. We're going to left rotate on node 5, the blue node. 5's right child, 10, the yellow node, becomes its parent. 10's left child, 8, the red node, becomes 5's new right child.
Ooh, okay. So, okay, this makes sense. This is basically the way an AVL tree works too. So I think we can simply implement, okay, so for now, as we are laying down the foundations of what our red-black tree class will look like so that we can use it in the memory allocator, I think we can start with this. So left rotate and right rotate. So how would this come about? So I'm just going to write down sort of, I'm writing all of these sort of separators just so we don't lose ourselves while we're developing. And for now, I'm just going to add one called rotations so we know where they are located. And let's think about this. Like, we want to create a function, so it's going to be probably void left rotate. And then we're going to need to accept some sort of red-black tree, but the red-black tree class is templated, so of course we need to add that there. And we have the template, we have a type name T, and then another type name for the comparator. And then this guy is what we're going to call the arbitrary, right? So, well, actually, I think it's better if we just call it node, because we want to think about it as a node inside the arbitrary rather than the whole arbitrary. Although it's almost like every subtree of a red-black tree is a red-black tree. That is not true, because if you start the tree at a red node, then you violate one of the properties, but it's almost true. But let's just think about it as a node. And if we want to left rotate, we generate this sort of motion that Michael Samble kindly points out. So how would we start this? First of all, where are we calling left rotate? Like, who are we calling left rotate with? Are we calling left rotate on 5, 10, or 8? I would argue on the root. Right? We sort of assume that the node we are given is taking the position of 5. So that's great. One thing we need to definitely do, and I mean, I'm not sure if you guys, like, it depends on the coding style. Personally, I like to include a bunch of asserts. I've never really done that as much, but ultimately I've been realizing how helpful asserts are. For those who don't know, an assert is basically just a way in which your program checks whether a given condition is true or not. And if it's not true, then it just finishes the program and terminates and tells you assert failed. So one thing we want to assert, definitely, is that the node, right, first to my right, is different from a null pointer. And we also want to assert that that node to my right, so in this case, 10, and then its left child, which would be 8, is different from a null pointer. Is this something we want? Well, actually, no, we don't want that. Because it is possible that, in this case, 10 could have just the nil child, right? Which is completely valid because we think of nil as the leaves of the tree, so that's a completely valid node, and it's of black color. So in this case, we only need that first condition, that the node to right is just not a null pointer. So perfect. We just include this here. Just if we ever call rotate on left rotate on something that just doesn't have a right node, we're just gonna complain and say like, dude, you made a mistake somewhere along the way. So this is gonna be there just while we develop, but it's not gonna be there forever. So that's a good thing. And let's see. Let me think. So we want to left rotate. That means that first thing we need to do is I'm going to write the comments based on this image sort of on the right, right? So I'm going to refer to their numbers 5, 10, and 8. And after that, well, we will sort of interpret what we have to do. So we need to make 10 the root, and we also need to make 5 be 10's left child, and we also need to make 8 be 5's right child. And other than that, it seems like everything stays the same, right? 5 still has 2 as its left child and everything. There's no way in which we can fail on this. Seems pretty straightforward. So yeah, I think it's only these 3 things. So how are we going to achieve this? Well, there is a sort of situation here, and it's the fact that when it comes to relationship between nodes, we are storing sort of a parent pointer, and then we have the left and right children. What that means is that if I want to update, say, node 10, right, and make it the root, I mean more like suppose this rotation was going on not in this sort of tree, but that like this is a subtree, so there's more nodes up of like upwards of 10, right? So what that would mean is that when we left rotate, we want to precisely make 10 the root, right? So what will happen is the parent of 5, the parent that 5 had previously, now needs to inherit 10 as a child. So for that parent, we need to update the right pointer or the left pointer. And at the same time, we need to update 10's parent pointer. So we always have to remember to perform these 2 operations sort of all the time. And that seems a little bit annoying, which leads me to think that we may need some helpers, some sort of like stuff that we can use to make the coding easier. And I'm thinking of adding a helper for a sort of a subordinate relationship. No. How could we? I think a good name for this could be link, right? To link. And then it could have something like give me the parent, sort of like the to be parent node, and give me the to be child, right? And we would also need to know whether you want it on the right or on the left, which I guess can just be a bool. So bool left, probably. Although we could also sort of take advantage of calling sort of both link right and link left, but I feel there would be too much code repetition for something so simple. So great. We want to make 10 the root, make 5 the 10's left child. Okay, this is great. So there is a little bit of a subcase I'm starting to detect here, and it's the fact that we want to update the parent's child pointer, but if the parent is null, in the case of where we are rotating the root, then we cannot do that. So we have to be very careful with that. So, okay, let's first proceed with this first step, which would be sort of making 10 the root. Let's do something like, okay, if the current node, right, doesn't have a parent, or has a parent, then we want to do something, right? And that's something. This is interesting because now this left rotate actually does need to return something. So what I'm thinking about here is notice that when the rotation happens, right, when you have like the 5, the 10, and the 8, the rotation happens, right? It turns to the left. And what occurs is that the 10 goes up, right? So suppose we had a pointer, something pointing at 5. Once the rotation occurs, 5 is no longer the root. But we want to still be at the position we were pointing to before. So our function needs to notify the user of who the new root is. So I think we are bound to return some sort of pointer to the new root, right? And so here we can sort of include a comment, some sort of doxygen comment, right? It returns a sort of pointer to the new root. I'm gonna call it root. Well, to the node that now occupies node's position. Perfect. I think that's a little bit more understandable. Yeah, perfect. And so let's continue focusing on this. If we do have a parent, then we need that parent. Well, we need to figure out, are we the right or the left child, right? And so the way to figure that out, left child, sort of, we are left, would be to say, well, am I equal no parent to the left? Is it equal to myself? Right, so am I the left child? Once we know whether or not we have the left child, we want to say, well, now make the parent left pointer or right pointer, depending on the situation. So I think sort of like if we are left, then we want the parent's left pointer. We want it to point to our new sort of the one that's going to be taking our place, in this case 10. And that would be the node's right child. And we also want to make it so that the node's right child has as parent my node's parent. Not only that, but I need my node's parent to, after this, be invalidated. So it's a little bit of a confusing scenario, right? Like, well, not really confusing, but like we need 3 lines of code to simply say, now make 10 be the child, right? So the parent, and by parent I'm imagining like a node that's up here. The parent, now its left pointer needs to point at the node's right, which would be 10. So like it's sort of like make 10 the root. Now 10 needs to realize that its parent, it's the guy that's above 5 in the image on the left. And not only that, but 5 needs to forget that that's its parent. So I think this sort of motion will be repeated constantly, because in the else, we just perform the exact same thing. It's just that we do this with in the case we are the right child. So it is the exact same code. It's just that now it changes that first line. Parent and then node parent. We need to forget about it. Not only that, but we can simplify all of this code by simply making it so that these 2 things that are the same on both sides, we can remove them and take them out. Perfect. So this is what the code should look like whenever we have a parent, so that we can make sort of our little guy the new root. But, this seems like rather confusing, at least to me. Like, we have 3 lines to represent the mere act of updating sort of a child. like that doesn't really make much sense. So that's why I proposed this helper. I'm not sure if you guys agree. If somebody has a better suggestion, put it in the chat. But for now, I think I'm going to proceed with this helper. So this will be, I want to link, and then of course this is going to accept nodes. So we need to template this function, and we need to make it a type name t, and then a type name comp. And then this link, we need to accept two things. So an arbitrary, we're going to be accepting a node, fine. And this node, it's going to be sort of the, once again, the to be parent, right? And the other thing we need to accept is what is the to be child, right? So to be child. Lastly, we need to know whether or not we are the left child, sort of the to be child wants is the left child or the right child. Right? We don't know which one this person wants us to put in there. So in order to do this, we're going to follow the exact same code. So this to be parent, we need to do a couple of things. So if we are left, sort of we want the to be child to become the left child of the to be parent, then what we need to do is, first of all, tell the left child of the to be parent, right? So to be parent left is different from a null pointer. We need to tell that left child that we are no longer its parent, right? So to that guy, the left child, we need to tell it that its parent, it's no longer us. Great. After that, we need to make it so that the parent, the to be parent, stores as left child the to be child. And we need to notify the to be child that we are now its parent. Great. In the case we want to make it a right child, then it's going to be the exact same code. It's just that instead of left, we're going to have to use right. Right? So tell the guy I have to take my right child that I will no longer be its parent. Then make my right child be the to be child, and sort of tell the to be child that I am now its parent. So does that make sense? I hope it does. Of course, these two lines are repeated, so for the sake of just simplicity, I'm just going to put it there. Can we perhaps make this a little bit better looking? Because it's, I don't know, it just seems like a little bit weird. No, I feel this is simple enough. So link, we can attach a description to what link does. And here I'm just going to say, well, it returns nothing, right? But it sort of links a to be parent to a to be, well, links to be child as a left right child, sort of according to the left parameter of to be parent, right? There's also a sort of side effect or like a remark, and it sort of like nullifies the parent pointer of the left right child according to left of to be parent. Great. Okay. So now we know what link does, and the way we can use link is that we determine whether or not we have the left or right child, and we now easily can simply call link, and we want to link what? The current parent we have with our right child. And that simplifies everything, right? Now, although this code is not that difficult to understand, we're going to be repeating this motion over and over and over and over again. So it's good if we have something like this, right? Where we simply say, well, link these two guys and pass it whether or not we are left, right? So perfect. I think this is great. And that is in the case sort of our node has a parent, right? If it has a parent, we need to point it to sort of the new element, which would be 10. So up until this point, oh, this is what we were drawing yesterday. So let's eliminate all of this stuff. So up until this point, what we have is in that picture, we have, I'm gonna hide the terminal. I don't know why I had it open. Brother, how can I close this window? This guy's a little bit annoying. That's okay. We're just gonna have, let's see, we have 5 over here. Then we have sort of 10. Then we have 8, and then we have 2. And I don't think, I mean, the other nodes don't really matter. And there's a parent pointing to 5, right? So I'm gonna draw little arrows here. What we have done so far is link 10 with the parent. So now the parent is pointing not to 5, but it's pointing to 10, right? 10 no longer points to 5 as its parent. It is instead pointing to that guy. And 5 has lost track of a parent. So that is great. What now we need to do is to make 5 10's left child, right? So what we need to do is to say, well, if this is the way things are, right, we need to make it so that 10, so in this case, the right child, first of all, forgets who its parent is, so that it's no longer linked to 5. And why do I do this? Well, because notice that this thing here, this only happens whenever we have, what's the name? Whenever we have something above 5. Right? If there was some other node that's pointing here. So this code doesn't get to execute at all if we have to take this scenario literally, where 5 is the literal root of our tree. So we need to make it so that 10 forgets who its parent is. So 10 doesn't have the little arrow, and we sort of kind of erase it. Bye-bye. Then we need to, and let me actually put this side by side, right? I feel that's a pretty good way to tell what we need to do. So we need 10 to forget about its parent. We need our node to have no right child. We need to sort of forget about it. I know y'all are looking at 8, and tell me 8 is its right child, and you're forgetting about it. Don't worry. For now, we're just focusing on 10. So we need 5 to forget its right child. So goodbye. This link is lost. And now we need to make it so that 10 sort of makes us its left child. So the left child is equal to us. Now there's a problem here, and a big problem. As the lines are written, we currently first make the node right a null pointer on 5. So now when we try to reference this here, this is going to be a null pointer, and then we get a null pointer to reference, and then absolutely horrible things happen. So we're going to first do this, right? We're going to make it so that the left child of 10 becomes 5, and then we make it so that 5 forgets about this, right? And in fact, I think we can simply sort of move these 2 lines that are about forgetting to the end. Now there's another problem, that when we perform this, right, node right, always have in mind that node right is 10, right? Because Node is 5. So let me actually write that down here. This is node. Oh, what the hell? Why is it so small? Why? Well, oh, there you go. So we need this to be like sort of large. Excel. Oh, well, yeah, I think I just did it in such a way that it's really zoomed out. That's okay. This guy is just gonna be node. Node refers to 5. Don't forget that. If there's anything you're gonna take away from the stream, is that node refers to 5. Okay? So after that said, node right is gonna be 10 in this scenario. So 10 changes its left child to be us, 5. But in that process, we lose track of 8. And there's no way, oh shoot, what's going on? Okay, we lose track of 8. Right now we've forgotten about 8. And what we can do is we can simply just save 8 in a variable. We can just say arbitrary conf pointer, and then this is going to be sort of our left grandchild, and that's going to be the node's right, and then we're going to take it to the left. Right? So that's going to be 8. We're saving 8. I'm just going to include a comment that this refers to 8. So perfect. We include this. We make this the sort of left. So 8 is still thinking that 10 is its parent, but 10 on the other side is now pointing to 5. Right? Sort of a left type of relationship. And once this is done, the only thing we need to do is nothing else. Oh no, never mind. We need to tell 5 that we are its parent. So now node parent should be equal to node right, which should be 10 at this point in time. And that seems great. So now what we are doing is basically grabbing 10, we're moving it up here. We're taking this whole structure sort of up here. Now 5 and all of these arrows sort of change. 10, its left child pointer is pointing at our node. And our node is now pointing to 10 as its parent. 8, completely forgotten. Like, now we no longer have that. So yeah, first need to unlink 10 from here. And this seems correct. Now the node to the right. Yeah, 5 now needs to forget about that. And now we need to update 5 to point to 8. Right? And we need to make 8 point to 5 back as its parent. And if you remember correctly, we've already created a function for that, which is link. We want to link our current node as the parent of who? Well, of the left grandchild. Right? Now, we could also use link to simplify some of the stuff here. And of course, we want it to be the right child. So right is false. Because right now we have it tell us whether you want it to be its left child or its right child. I want it to be the right child, so it's false. And let's see, the way things are right now, I think we can simplify stuff a little, because currently I'm making the node, so 10 points to node as its left child, and my node points to 10 as its parent. So we can simply apply link here too. We can say link who? Well, the node to my right, which would be 10, as the parent, and I want the child to be myself. Perfect. I think that sort of simplifies things a lot, this link function. let's see. If we have this, and this would be, I want you to be my left child. So let's see what would happen in that case to see that we're doing the exact same thing as here. Currently, right, we make it so that if left, right, the to-be parent left is different from null pointer. That is true in this case. Then we want to forget about that child. Yes. Then the to-be parents left is now the to-be child, and then perfect. Perfect. This makes a lot of sense. And it is the exact same code. So now we've simplified it like quite a bit, if you ask me. Great. Great. This is great. Let's see. I think we can now this actually should be over here. So there's something I'm trying to think of, and it's whatever this line is doing, we just have to do fix this BS. Like I don't know how else to. Like this little line is a little bit confusing on what we're doing because it really depends on whether or not we have a ghost parent up here. So if our parent is different from null pointer, right, and we are whether or not we are the left child or right child, I just want for my node's parent, so in the case of 5, my node's parent to become this guy on the right. Oh, sorry. For my parent to have this guy on the right as its child. And I become completely forgotten, and yes, perfect. This makes a lot of sense, I feel. Let's just make sure that it works. So if we are to believe ourselves as having the tree on the left, then what we're going to see is the following. We're going to have, let me actually scroll back to content, and I also want to zoom in a little bit more because right now we're kind of far away. Yes. Okay, perfect. But I want a medium size one. Want a medium size? Hello? Hello? What is happening? Medium. There we go. Okay. So we're gonna have 5, then somewhere in here we have 10, then we have 2, then we have 8, and then we have 12, and then 8 has 6, and it also has 9, right? And they're all connected by sort of these arrows, right? 5 points there. Is there maybe a shortcut for this arrow? No. Okay, that's fine. 5 points to 10, 10 points to 12, 12 points to 8. Oh, actually, I think I'm just going to use the pencil. Kind of lazy today. Whoa, why is it so thick? Stroke width. There you go. So, perfect. 5 points to 2, 5 points to 10, 10 points to 12, 10 points to 8, 8 points to 6, and 8 points to 9 also. And not only that, but they are also pointing back to their parents. Right. Okay, perfect. Let's run this. If the node's parent, so suppose that there's some sort of, right, this is some sort of a subtree of an overall red-black tree. If the node's parent is different from null pointer, that's the case, right? We do have a parent. This one's node, right? For those who know, this guy is node. So if the node's parent, right, we detect whether or not we are a left child or a right child, whichever one, and then we link that parent with the node on the right. So now this parent won't be pointing at 5. It will be pointing at 10, right? So it will be just 10. Great. That's awesome. Now, we need 10 to forget who its parent, that like 5 was its original parent, but we'll take a look at that later. Now, because 10 already knows that this new guy is its parent, 10 also forgets about 5 being the parent. And now we store 8 inside this variable. And what we do is, to the node on our right, which would be 10, we need to make it the parent of the current node. How does that work? Well, we're going to have 10. I'm going to move it up here just for the sake of sort of visuals, right? I'm going to move the arrows too. Right? 5 is still pointing at 10 as if it was its right child. So it's still the right child. And what we have is link 10 with 5. And link simply does, okay, so the to-be parent, which is 10, does it have something on its left? Yes, it's 8, right? And if it does, then I'm just going to tell it to forget about me. So bye-bye. 8 doesn't know anymore who its parent is. After that, we're going to say, well, the to-be parent on the left is going to be equal to the to-be child. So now my left child on 10, it's going to be 5. Great. And then after that, the to-be child, which is 5, it's going to have as parent the to-be parent. So 5 forgot about who its parent was, and now it's going to have 10 as its parent. Notice nonetheless that 5's right child is still pointing at 10. And that's what the next line fixes. Now we want to link node, which would be 5, with its left grandchild, which remember, it's storing 8. And we want to link them together as sort of a right child relationship. So what it's going to do is it's going to say, okay, the to-be parent is 5, and then 5, does it have something to its right? Right? The answer is yes. So what it's going to do is it's going to go, it's myself, then my right part. Ooh, we have a bug in the code. I have a huge bug in the code because according to how things are being managed right now, this thing, okay, so link always assumes a well-formed tree. So it's a bit of a problem. I think a way in which we could solve this is simply get rid of these lines where we sort of tell our previous child that we are no longer its parent. That is nonetheless a little bit dangerous. It seems like it could play us a bad, it would give us a bad time, but I think it's a reasonable thing because after link, you sort of have to assume, this is difficult. Well, no, not like difficult, but like it's an important decision we have to make. So, do we want to do we want to have the invariant that after every single time link is called, it must be called with a well-formed tree, and it will also return a well-formed tree? I mean, that would be very beneficial, right? But can we fit that in our code? Yeah, because now the problem is that Node still has the right guy as its child. So I think we can preserve things the way they are. Assume sort of that link will want a well-formed tree, and then we need to sort of, because there's no way for link to realize that this is the right child of Node, right? Like it just doesn't, it doesn't happen. We could embed that into the function itself, but I do not think it is a wise decision. So assuming that now we make 5 forget about its right child, we're gonna have this, right? And now when we go here on the link node left GC, then we're gonna say, do you have a right child, Mr. 5? No, I don't have a child. And then we say, okay, Mr. 5, to your right, you're going to have 8. That is the to-be child. And left GC, which is storing 8. And then after that, we tell 8 that its new parent is 5. So great. 5, you're going to have 8 as your new right child. And 8, you're going to have 5 as your new sort of parent, right? So now, hello? Well, now the tree is in the state it should be in, which is 10, 5. 12 is still, 12 we didn't touch at all, so 12 should still be 10's right child. 5 is here, 2 is here, 8 is here, 6 is here, 9 is here. Everyone knows who the parent is. Everything has been preserved. Awesome. We have a left rotate. So the last thing I want to analyze is what happens when there's no sort of ghost parent. That is what happens when this line of code is omitted. And what will happen is, let's see. So we have 5, right? Then the left-hand child is still 8. Then we link the node to the right with the node, with a current node. Yes, that is the case. So there's no sort of updating of 10's parent. Okay, I see. So node parent, I think we simply need to make it so that node right parent is equal to null pointer. So now we know where this line came from, and that sort of simplifies things, right? Yeah, I feel like that makes more sense. Let me think. Yeah, I feel this is a good recollection of what we want. I'm wondering. See, the only thing I'm wondering is like, is link sort of the correct layout, right? Should link be doing this, of like telling the previous child that it is no longer a child? I think the answer is yes. I think the answer is yes. I think they, this is gonna combine us in the foot later. Like this is gonna be, we are hurting ourselves with this function. But trust, it is going to work. Don't worry. So just remember what link does is it links a to-be parent with a to-be child. So it creates the 2 arrows in between them. Great. So now what we want to do is, that is left rotate. And then I imagine that right rotate, it's just going to be the exact same thing. Michael Samble, what do you have for us?
N's parent.
Okay, it is the exact same thing, just in the opposite direction. So I think that one we can code more easily now that we have sort of a reference, right? So we have an arbitrary, then we have t, we have comparison, and then we are going to return a pointer. Oh, we need to return something. We need to return the new sort of root, right? And that is going to be node's parent. Perfect. All right. So right rotate. And then what we accept is an arbitrary that is going to have t and component, and then we're going to accept the node. And we're going to do sort of all of the things that we've been doing so far. We first need to assert that the node to our left is not a null pointer, because if we don't do so and our left is a null pointer, then the root of the tree is null, which just makes absolutely no sense. Then we want to update our left child to have no parent. So we sort of unlink the left part of a tree, right? At least from the perspective of the child should have no parent anymore. Now, if our node has some sort of parent, then what we need to do is we need to determine whether or not we are the left child of that guy. Node parent left. And in that case, no matter what happens, we want to link together. So we want to now make our left child the new parent. So we're going to make our parent have as child the node to our left and tell that we are left, right? Perfect. So now what we want to do is we're going to make the current node, so in the picture that would be 10, we want to make the current node become sort of the right child of the new sort of root. So what that's going to imply is that 10 is going to lose its reference to whatever 8 was. So we need to store the right grandchild. Right? So it's a grandchild, and it would be like right here, right grandchild. So that'd be the node to our left and then to our right. Right? I feel like right grandchild is not a great name. I think left-right grandchild is better. And here it should be the right-left grandchild. Right-left grandchild. Perfect. All right. So now what we want to do is we have that stored over here. So now we want to link together who? So 10, in the case 10 has been linked with 5's parent. In the case there's no parent, sorry, with 5 has been linked with 10's parent. In the case there's no such parent for 10, this line is skipped, so the tree hasn't changed up until this point. And what we want to do is we want to link 5, so the node on our left, 5, we want to link it with 10, so the current node. And we want it to be the right child, so we pass it false. Perfect, so now they're linked together. Now, 10 is still believing that 5 is its left child, because this just makes 5 the parent, yes, and 10 is aware that 5 is its parent, but it still has that remnant sort of 10 believing that it still has 5 as its left child. So now we're just going to tell 10, no, right? You don't have a left child anymore. And after that, we're going to say, well, now that 10 has no left child, we need to make its left child 8. So we're going to make 10, the node, have as child the left-right grandchild, which we had stored before. And we're going to make it true, because we want it to live sort of to 10's left. And after that, we just simply return who the new root is, and that should be the node's parent. Perfect. All right, it seems like we have completed left rotate and right rotate. There's only, so okay, I'm not sure if somebody in the chat has experience with this, but testing, right? we need to test that these rotations actually work. Like I just want to be able to input a tree. I want it to give me the result, and then we can just inspect it to know whether or not these things are working. Because we have made so many changes and there's like so many details, there's so much potential for a sort of null pointer dereference somewhere that we definitely need that. So what I'm going to do is I'm going to add a file here called test arbitrary h. And okay, I've never really done testing. I hate testing, but in this scenario, we do need it, I think. I'm going to include sort of a function. Actually, this function will return a bool. It's going to be test. Let's test the left rotation first. Test the left rotation. And what this is going to do is it's going to be a function that is executed inside of main. And the only thing we want to do is simply say, sort of like, if this test left rotation doesn't pass, then we're going to say, we're going to print to console sort of like, failed left rotation. And then we're just going to print an end of line. And, of course, we need to include stream. Great. What? Include errors detected? Oh, okay. Yeah. A little bit of a slow, our little parser or whatever is a little bit slow here in VS Code. And after all of them are completed, we want to say, well, congratulations, you passed all the tests, right? Success. And then with a little, face with glasses. Yay. Yay. Perfect. So that would be the end of line for us. And everything should be fine. We, of course, need to return in this scenario. So what will test left rotation have? It will have a couple of stuff, but first we would need to have sort of this red-black tree of H. And what we're going to do with it is we're going to create a new red-black tree, and it should have int, and its comparator should be std less for integers. And I'm just going to call him arbitrary. Great. And what we're going to do with this tree is it's sort of needed to have elements. So I'm going to insert into it 0. Well, actually, I think we can. I don't think this is a way in which we can sort of test things because we haven't even implemented insert. We haven't implemented a bunch of stuff. I think we're going to have to part from a sort of array, right? The array representation of the tree. So for that, I think we can simply go and include vector. Perfect. And then std vector, all I want to do is, this is going to be sort of my tree, right? So this would be a binary search tree. Well, let's not do that. A tree, right? Normal. And then I want it to have the following elements. So return true. Here's in we passed. Which elements? So if we just perform the pre-order traversal of this tree, we can represent it. So for left rotate, I think we can go back to the picture and just find the pre-order traversal of this tree on the left, which should be 5, 2, 10, 8, 6, 9, 12. Great, so that's our representation of that tree. And we want to call sort of left rotate. We want to call it on tree for some sort of index. We want to call it on 5, which is the root, so 0. And for now, see, I think it's a little bit difficult to test this. No, I think I misinputted the name. Okay, great. So I mean, does anyone have an idea on how we can test our left rotate function? Because it's depending on the arbitrary class, right? But the arbitrary class is currently like empty, right? Like there's no way we can represent a tree with the arbitrary class yet. And that is a little bit worrying. What do we do? What do we do? I think we're sort of bound to not being able to test it until we make the arbitrary class a little bit functional. Right? Like until we make it have like at least some sort of, you know. I don't know. Let me think. Left, right parent. Actually, no. I mean, what am I talking about? We can simply just modify the pointers themselves, right? We can just we can just create the tree ourselves. Why didn't you just stupid? Like, what? I mean, yeah, right? Like we can just create our RB tree. So I'm just gonna put 5. Well, 5. No. And then I can just make 5.left be equal to a new arbitrary node that is just going to have 2 as a value. So this would be like 2. See, but then that means that we need a constructor over here that accepts arbitrary constructor that accepts some sort of value, and then we'll make this data be equal to that value. Great, sounds about right. So now we create that 2. Okay, 5 should have 5 as its data member, and then to the right of 5 we have a new node that is going to be 10. Let's do an int, and then we want it to be 10. Then after that, we need 10. Well, I guess I should have just created them. Yeah. 1, 2, 3, 4, 5, 6, 7. Okay. So 5, 2, and then 10. 10 when we have 10 over here. And then 8. We're name it 8. Then we need 12. We have 12. And then we need 6. 6. We have 6. And then we need 9. And we have 9. And now we just need to perform the sort of relationships with each other. 5's left is 10. And actually, I think this is where link is going to come handy. Link 5 to be the parent of 10, because we need to update 10's pointer as the parent. Link, and we need it to be what? 10 is, well, link it with 2 first, and then it's going to be its left child, so true. Then link 5 with 10 and make it its right child, so false. Then link 10, make it A to be its left child, so true. Link 10 and 12, make that be its right child. And then link 8 and 6 to be its left child, so true. And finally, link 8 to have 9 as its right child, so false. Great. Okay, we have no instance of function or whatever. That's mainly because, let's see, it matches the argument list. Could not match arbitrary comp against. Oh, of course, because all of these are expected to be pointers. So we just pass that guy. So you, and you, and you, and you. That should fix it. Awesome. All right. Yo! To the one viewer watching, we did it. Okay. Great. So I think we can link all of these guys. Hopefully that makes our tree what we want it to be. And then we can just test left rotate. So we just call left rotate, and we just call it on. We just call it on 5. And so we can pass 5's pointer, and then we simply print tree. And then we see what comes out of it. So I guess that like we need to store this in some sort of vector. A vector of integers, sort of like vector tree, the tree but represented as a vector now. And I think that now what we can do is I can just include. Well, actually, this is really not a responsibility of RB I'm still gonna include it though. I feel like include vector here should not be a responsibility of the class, just to maintain separation of concerns. We're just gonna have it as a helper, and of course, as always, we're gonna have a type name with t, and then a type name for comparison, and then we're gonna have a void on what printing or like sort of arbitrary2 vector is, and it should be a function that accepts an arbitrary, a red-black tree for comparison, and then we're just going to call it arbitrary. And then it also should accept some sort of place in which we can store the things we want. So this should be the standard vector that should store things of type t, and it's going to be the result. And of course, as always, we pass it as reference because we're responsible with our memory. And what we want to do is we simply want to say, well, vector, or, well, I didn't assign it a name, did I? Oh yeah, I did. Okay, so what I want to do is to say result.pushback. We're going to push back the current node, arbitrary. And then what we want to do is we want to call arbitrary2 vector with the current child, so left child, and then an arbitrary2 vector, and we want to do it with the right child. Perfect. So this should only happen if we have an actual left child. If arbitrary left, and if we have an actual right child. So that should give us a pre-order traversal of a tree. We don't return anything because, I mean, we're just gonna provide it the vector itself. So this should be arbitrary to vector, and then we pass it the vector tree as a result, and we pass 5 as our red light tree. That should be it. Let's see. No instance of template matches the list. Arbitrary vector against. Yeah, because this has to be a pointer. Sorry. Let's see. Hopefully, no. Error while processing. No matching member function for call to pushback. Brother, what are you talking about? Pushback is a vector function. Instantiation of function template specialization. No conversion from arbitrary int blah 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 to const value type for first argument. What? What's this error? Why are we oh, of course. Arbitrary dot data. Oh, yeah, we need to pass in the data for that. Perfect. So all I need is as a vector for a vector that stores integers, and that's exactly what I'm passing. Why are we line 121? Yeah, arbitrary data. Data is, let's see, if we rerun the code analysis, maybe it will go away. No, we have some error. Where? Arbitrary to vector. Oh, 122. Oh, of course, we need to pass in result. And then result. Perfect. Will it get fixed now? I think we need to rescan. They really don't like Visual Studio Code's thing with C++. Because it's, whenever you work with like templates and stuff, it starts to get really annoying. The left operand of. Ooh, so it's telling me about a mistake that may happen with the main function. Calling test left rotation. Okay. Then on line 7, calling constructor for arbitrary. Yes, returning without writing to this left. Well, I think this is just, I mean, of course it's gonna, the warning's still gonna be there, but we want this to check whether or not we are a left pointer. I think the logic is sound, but I'm not sure why it's complaining. I think we will discover that then, if there's something wrong. For now, what we are going to do is I just want to print sort of each number inside my vector tree. And then I'm just gonna see out that number and then create like a little space. Perfect. And then after that, we simply create a break of line. Like see out and line. Let's wait for VS Code. Great. Okay, it passes it. It does everything. So I think we are good to go. There's definitely going to be some sort of seg fault. I'm going to hide this corridor for a second. G++, we wanted to use, what is our file? Yeah, well, actually, I just want to cd into arbitrary. I think it's better to do it this way. So G++, please compile test arbitrary, and the output should also be test arbitrary. And yeah, I feel that's PVP. No, .h actually. An output test arbitrary. Do we want debugging symbols? I don't think so. I think we can just do this. C header input at C++ header when the C++ this behavior is deprecated. Okay, sorry about that. /test arbitrary. Permission denied. Okay. Shema, sort of plus x. Where is the plus in this keyword? I think it's this way. Test arbitrary exec format error. Test arbitrary doesn't have. Oh, why is this a .h? This should have been a .cpp. Why? Why? Okay. Yes, you're right to correct me on that because it's named as CPP. Great. Now it should work. Boss error. Guys, we have a huge problem here. Let's figure out what the problem is. G. Let's create the debugging symbols and stuff in our launch.json. I think we can just not go by tree, but arbitrary slash test arbitrary. Great. I'm gonna eliminate all of these things because this is the template I usually use. Programs this guy. Seems correct. Let's simply run it. Thank you. Let's see. Let's wait. We have a boss error, which seems like a rather weird bad access. We have a bad access. Okay. Why do we have bad access? We have it on the initial link. Okay. When you call test left rotation, right? What we're doing here is I understand what's going on. So there is an assumption that I'm making, and it's the fact that whenever these guys are not initialized, they're going to be initialized to null pointers. But this is completely false because we cannot really predict the layout of memory. So they could be garbage values, and I think that's exactly what the thing was warning me about. So I'm just going to call it red. And then data, it's just going to be something, and the comparator is something else. Great. I think that now, if we compile again, we're going to be able to see the result of what we want. So sorry, this is not the console I want. It's this one. Okay, brother. Then let's not initialize it. Okay, that's fine. Retrieve. Great. You said that. And let's call test arbitrary. 52869 and 10 is just gone. Oh wait, no. Never mind. No. Because we don't need to print 5, right? We need to print whatever this guy returns. Oh wait, we may have done it. Person in the chat, like the one viewer I have, we may have done it. This is great. So let's see if our rotation worked or not. So int stls res is going to be equal to this, and this is going to be a pointer, and then all I want to do is, rather than having that, I want to print res. Okay, perfect. Want to reset, and we want to execute this again, and then we want to run it. Let's see. 10, 5. Where is 12? Oh, no, that's great. 10, 5, 2, 8, 6, 9, 12. Oh my god. We achieved it. Yo, let's go. Okay, perfect. This is awesome. So that would be our left rotate. Now let's try. So this would be our test for the left rotation. let's now create a test for right rotation. I do have a question though. Can equals be used with C++ vectors? This is such a basic question, but I don't know. I just don't know it. Comparing vectors for equality, and the answer is yes. Okay, perfect. So I think that what we can do so that this actually behaves like a test is we can simply say that we are expecting sort of, or like assert, right? We need to assert that like the arbitrary to vector, oh sorry, that the vector tree is equal to a vector of integers that just has the thing we expect, which should be 10, 5, 2, 8, 6, 9, 12. And that should be it. We of course need to include cassert over here. Great. And that should be it. Hello, C++ language server, are you there? Well, std of course. Hello. Identify vectors undefined. What? Hello. What is going on? Wait, everything is fine, no? Okay, I mean, vector of integers, we're just gonna call it expected. And then it's gonna make it equal to these guys. There cannot be anything wrong with this then. What? Too many arguments for, oh, okay. That's this low. CG++. Great. And now we're gonna, moment of truth, ladies and gentlemen. Success. Oh, I missed an S. Oh. Yeah, that's embarrassing. Okay. Perfect. Awesome. So I think, yeah, success. Okay, our test passes. We coded left rotation correctly. Now we simply need to add the test for right rotate. And in the case of right rotate, I think I'm just going to do the exact same thing. Let's just create a sort of like expected vector. Is expected. And then we're just going to make it equal to whatever we expect. Because after the right rotate, well, actually, I'm going to stick to the same tree. After the right rotate, you would expect, let's see, if we were to right rotate this, it would be something like 2. Actually, let's stick to what the video gives us as example, and that would be the tree sort of on the right. Yeah, there you go. So it would be link. So here, instead of this, we're gonna have, we need to link 10 as the parent of 5. Sorry, it's supposed to be letters. 10 as the parent of 5, and we want it to be on the left, yes. Then we want to link 10 as the parent of 12. And then we want it to be on the right, so false. Then we want to link 2, we want to link it to, well, sorry, 5, we want it to be the parent of 2. We want it to be its left child, so true. And then we're going to link 5 to be the parent of 8. 8. Then we want it to be the right child, so it's false. And then finally, we want to link 6, 6, and we want to, 8 to be the parent of 6, 6. And then we want it to be its left child, so true. And then we want to link 8 as the parent of 9. Yo, awesome. Let's go. So, so now that we have that, we want to run a right rotate on 10. And what we expect is precisely the thing that we see on Michael Semble's video on the right, which, no, I don't want to see that. I don't want to see that. I don't want any pseudocode. Thank you. Okay, sorry. Great. Okay, it should be 5, 2, 10, 8, 6, 9, 12. Right, that should be the end result. And we simply assert that that's the case. Enter tree equals to expected. Great. Reset this. Well, we would need to call, since we're using asserts, I think this is just not needed. Test left rotation, test right rotation. Test the right rotation. It should also have a semicolon and success at the end. Perfect. Reset the terminal. We recompile. And once that's done, reset again, and then let's run the program. Success! Yo! We did it! Great. Okay, it seems like right rotate also works. Perfect. There's only one last piece that I want to test, but I think with this we have a good sort of basis for what we want and have. So it seems like the functions work as expected, which is great, and we can be a little bit sure about it. Not completely sure. I myself am not completely certain about it, but I think they are sort of a decent baseline, to say the least. So we have left rotate, we have right rotate. Okay, now what goes next? I'm not sure. We've been on stream for an hour and a half. Damn, that's a lot of time. I'm going to take a break. Only a break for probably 20 minutes, 15 minutes. So to those two viewers, I'm going to take a break of around 15 minutes. And yeah, so we'll be back at 4:05 in PST time. So I'm not sure where you're watching from. So just add 15 minutes to the current time. And then we'll be back. All right. See, now I set up OBS Studios, and now I can like switch to like a little screen, like this. Wow. Okay. We are starting in 15 minutes. Okay. I'll be back. Hello. Yeah. Okay, perfect. Awesome. Hello, everyone. Welcome back to the stream. Took a break for a little while, 15 minutes. We're back on track. And it's time to continue with our programming of red and black trees. So hopefully we can get that done today. We're going sort of slowly but surely creating the red-black tree. This is something that takes some time, mainly because we want to be really careful. There's a lot of pointer manipulation. There's a lot of dereferences. There's a lot of passing pointers around. And that is going to create a lot of errors for us. So bear with me. Be very patient. But I hope to explain my reasoning sort of more clearly. And yeah, I mean, let's go. Let's continue. So I'm going to transfer to the coding scene. Perfect. All right. This is awesome. So we had just left on, let me reduce the line here. We had just left on us trying to test both left rotate and right rotate. We tested them and it seems like they work. We're not completely 100% sure. You can never be 100% sure. But we are confident enough that we are able to move on. Okay? So the natural next step would be, of course, insertions, right? So if we're going to insert stuff, we're going to need sort of, we're going to need to be a little bit careful with a lot of cases and a lot of stuff. Insertions are, if anything, really annoying, extremely annoying. So yeah, there's one that I feel I'm thinking of, and it's how will we want to design this, right? Do we want our red-black tree class to be sort of a per node class, that is, every node is an RB tree, or instead have a huge class called RB tree, and then have like classes called nodes? The reason I ask this is just because of the way everything is going to be organized. I'm leaning more towards the second one, because not every node or not every tree starting at a given node is a red-black tree node. Because there's going to be red nodes and those cannot be roots. So I think we're going to have to perform that separation of concerns where we create a node class and everything inside our RB tree is just that. I'm trying to think, for the purposes of our memory allocator, would that make any sort of difference? Right? Because if we have an RB tree class, I don't think... Yeah, I honestly don't think it's going to make any sort of difference. So we can simply... Yeah, okay. We can simply proceed with that. So let's create a little class of called node. And the node class is, of course, going to be completed. Going to be completed with a time node t. But this guy is not going to have much to it. All we need is precisely all of this information, except for the comparator, because the comparator is just doesn't belong to us. This is not going to have any methods or anything like that, so just for the sake of clarity, I'm going to name it a struct. And of course, the struct. Well, I do have a bit of a question, so pardon my ignorance, but I'm trying to precisely learn sort of all these details about language. And I think structs can definitely be templated because like a class is just a struct. I'm not completely 100% sure, but I'm pretty sure. So part of my ignorance is that's not the case, and we discover that in the future. But yeah, okay, we're gonna have the node class, and this guy should perhaps go up there just for the sake of code of gun or organization. I'm going to put it right here. Great. So we have a color data and all of that. For now, so there's a sort of to-do list that we need to keep track of. Things that we need to do is apply ZM's optimization for color. If you don't know who ZM is, ZM was one of our viewers yesterday when we were trying to come up with ideas for the memory allocator. And he suggested that the color bit can actually be encoded in the last 2 bits of the parent pointer, mainly because memory addresses are going to be 4-byte aligned. So we don't really care about the last 2 bits, which is a great observation. We have yet to do that. We will do it. But for now, let's just treat it simple and sort of get all the logic out. And then we're going to modify the random black tree once we put it inside the allocator. So for now, we are going to, inside a red black tree class, store a pointer to the head of a tree. Or, well, I feel in the context of a tree, root makes more sense. Right? So this is a node start, and yeah, I feel that's kind of it. Now the red black tree doesn't really accept any sort of data value. The only thing would be this node, and I mean, just for the sake of completion, I guess, we're just gonna make it so that this guy sets its data equal to the value. Perfect. So now inside of RB3, we need to change all of this stuff, where rather than this, I think we're just going to need a node int. I feel this is better. And inside of link doesn't really care about whether something is a red black tree or not. So it should be node. Node, and then we get rid of that comparator, and then we just do this. And everything should stay exactly the same. For the arbitrary to vector, we do want sort of an arbitrary. Well, actually, no, we want just a no. Star. I think that completes our quest, right? Because here, link should be requesting pointers to nodes, and that's exactly what's going on. Yes. And then, okay, why are you failing? No matching function call for link, can the template ignored, couldn't infer template argument comp. Oh. Yeah, we don't need the comparator anymore. Same over here. Awesome. I think we're ready. Let's wait for the language server to update. No matching function called to left rotate. Okay, line 56. Oh yeah, left rotate is still expects sort of a red black tree, but I think that instead of that, we're just going to return. It's going to be working with nodes. There's no need for a comparator, and the node is the only thing we need. Perfect, and same sort of thought process applies to this guy over here. So we apply the node and the comp, and then node, and then comp, and I think that makes it for us. Let's just check in here to see if this guy's happy or not. A value of type node int cannot be initialized as an entity of type arbitrary. Blah 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 blah. Of course. So we need this to be a node int. Great. And arbitrary to vector, and everything is fine. Okay, awesome. Now we just need to convert this to node int. Node int. Act. And then link is gonna just fix itself. This guy is the last one we need, where this should be a node of integers. Awesome. That should solve it all. Great. We only have one more error. So 0 while processing. Use a class template node requires template arguments. So arbitrary h45. Line 45. So over here. Oh, you mean for the root. That's just going to be t, because we already know that. Oh, another viewer. Hello, viewer. We are coding currently a red-black tree because we're going to use it in our allocator. So yeah, we're just, let's see, use of monocle identifier comp, line 67, and then on line 90. Of course, this should be a node t only. And what else? I think that's sort of all we need. Right? Is there anything else? Line 67. I think it's the same mistake. Yes. Okay. So this should be, instead of a red black tree, this should be a node. Let's see. Awesome. Everything should be fixed now. And C++ language server. Yes. Okay. Great. So now what we're going to do, hopefully, is we are going to find, okay, we have everything we need. Let's see, rotations, right? We're done with them. That's good. Let's add a description to this sort of add brief left rotates the given, no, the tree at, or like the tree left rotates trees, no, right? It's like, and then same here, left rotates the trees starting at no. The helpers we don't really care about that much, except for link, but link we have verified already. And I think this is great. Now we proceed. What is the next thing that we must do for a red black tree? Well, we already have rotations sort of there. Now we need to focus on insertions. And insertions are going to be a pain, as I said before. But now that we have changed everything to instead be sort of like the red black tree is sort of the general class. Whenever we find something, it should be a T. Okay, insertion. It's gonna be difficult, but let's begin. Okay, so to insert, right? How do insertions work on a red black tree? I think we have here Michael Samble's video on red black trees.
Today we're going to learn about red-black tree insertions. In this video, we'll focus on strategy. And in the next video, we'll do a few examples. Here are those properties.
We have the properties of a red black tree.
We've covered them previously. And D is Z's uncle.
Okay, so right off the bat, we're going to have to keep sort of terminology for parent, uncle, grandparent. We already know the parent. We don't know grandparent and uncle, but we can derive them from the information we have up until this point. That is, grandparent is just the parent of the parent, and uncle is going to be if I am a right child, or if my parent is a right child of my grandfather, then the left child of my grandfather is going to be my uncle. Like, it's going to be a bit of a complicated mess. But
goes into a red-black tree and color it red. We know eventually.
Let's see. So the strategy for insertion is, let's see, insert Z, which is just the node that we want to insert. Color it red. Okay. Then recolor and rotate nodes to fix the violation. Okay, so every insertion is red. And whenever there is a violation, we need to recolor and rotate. Right? So, great. Now, the strategy is this. It seems like we have 4 scenarios. Yes. Okay, these are the 4 scenarios in a red-black tree. And Michael's going to go in detail for each of them. K0, root, whenever we insert something, and that something happens to be the root, we need to change it to black, because one of the rules is precisely the root and leaves are always black. So in order to account for that, let me simply Okay. We need to initialize the root to be a null pointer. Oh, sorry. I have caps lock activated for some reason. Null pointer, yeah. And then we need to insert something. And that something is going to say, okay, if the root... So I guess it's better if we simply comment case 1 or case 0, right? New node is root, in which case, just make it black, right? So what we're going to say is, well, if the root is just a null pointer, that is, we don't have a root yet, then we need to create a new node, and that node is simply going to have the following things. Where is the node? Construct. Where is the node struct? There you go. Left, right, parent, color, data. Okay. And so I also need another constructor here that allows me to simply include the data. And then, let's see. Do I need anything other than this? No. So we're going to have the color, right? And then we're going to have the value. And then the other stuff we can just figure out ourselves. Our data will be equal to the value, and the color is also going to be equal to, sorry, this color will be equal to the color that they pass to us as a parameter. Color, just for the sake of memory alignment, we're just going to have it up there. Let me think. Yeah, I think we're good with this. It seems right. And great. So now we have color and data. And what we want to do is we want to say, well, let's initialize this to be of red color. Well, sorry. If this is the first thing you're inserting, it should be black. And it's going to have as value val. And perfect. We simply return. That's the only thing that we need to do whenever we are on case 0. For the rest of cases, it becomes a little bit more complicated, right? Because we now need to account
Z's parent,
there you go. So
grandparent, and uncle. When Z has a red uncle.
Okay.
For this situation, we recolor Z's parent, grandparent, and uncle.
Okay, so we have another case 1, where Z.uncle, yeah, let's call it Z. Z.uncle is red, or Z's uncle is red. So we need some sort of function, or like a way to extract the uncle without it being so awkward. So I think that what I'm going to do is, inside of helpers, we have link already, we have arbitrary to vector, but instead of link, I think I'm going to include sort of family members, right? And then we're going to make sort of an uncall function. So we need to template this as MNT, and then we're going to return a pointer to what we will call the uncall. And in order to retrieve an uncall, we need to have a reference of who we are talking about. So that specific node, I need to know about it, right? And what we are going to return is, it really depends on sort of bool is parent left child. Then we're going to say, well, my grandpa, right? So is my grandpa's left child equal to my parent? If so, then my parent is the left child, right? So if my parent is a left child, then that means that we are going to have to return what? Well, my parent is the left child, it means that my on-call is going to be my grandpa's right child. So grandpa right is what we return. Right. Otherwise, we're just going to return my grandpa and it's right. Sorry. My grandpa and its left child. Great. So awesome. I think we can simply condense this into a little ternary operator. And then we simply say right. Otherwise, we return grandpa of my node, and then left. Perfect. And that way we can skip this. Awesome. We have the on-call, but as you can see, we also refer to a grandpa function. So we're going to create that. And although these are like pieces of code that are very short and small, they are going to become extremely frequent, and we're often going to have to use them in conditionals and stuff. So it is better if we just sort of create their own little function to help, just because it's going to be annoying. Right? So return this node's parent's parent. Great. We have it. So we have these family relations on what the grandpa of a node is, on what the uncle of a node is. And what we're going to do is we're going to use them here. So you'll see that it becomes way simpler now, because now I say, well, if Z's uncle is red, right? If the uncle of well, actually, what am I talking about? We first need to insert the node. So this is just for sort of error or like conflict resolution. Those are like the cases. So whenever we insert, we just want to insert normally, as we would in a binary tree. It's like a little guy. Okay. Let me drink some water. Have been talking for a while. To new viewers, we are creating a red-black tree that we're going to use on our memory allocator. So we're getting familiar sort of with the red-black tree concepts we're creating and all of that stuff. So let's see. We want to insert something in a red-black tree, and this is just going to work the same way it always has, where we are going to say, well, if I am going to the, I'm currently looking at the root of my tree. Right, I think we cannot do this recursively, so I'm going to have to store some sort of variable of what the current node is. Then we're going to say, well, if the comparator, right, tells me that the value of my current node together with this value and the data of the other node, should be an arrow, is there, then what we're going to have to do is comparator always returns whether or not something is smaller than another thing. So here, if val is smaller, then we need to go to the left, right? So cur would be equal to cur left. Cur left. So while we'll sort of, well, I need both cur and prev. So there's that. And then while the current one is not a null pointer, I'm going to perform sort of all of this paraphernalia. Where we have this, great. So if the value is smaller, then we have, yeah, seems about right. So now while the current one, no, if comrade, okay, the value is smaller. I'm gonna say, well, this should go here. If the value is smaller, then I want to make the current one equal to the current one's left. Otherwise, we want to go to the right? Now, by the moment this thing becomes a null pointer, it means that we have reached a leaf. And it means that we can insert our node in there. So once that happens, we also need to keep track of prev though. So prev would be equal to here. Prev should be equal to the current one. Great. And so what we're going to do now is we're going to say, well, we have reached a leaf. So what we're going to do is we are going to say that the previous node, the one we visited right before sort of defaulting, is going to be the one we insert ourselves into. So if comp of the value in the previous node's data, I think we're going to have a lot of code repetition. So it's better if we modify stuff a little. So instead of comparing this, if the comparison between the two is this, right? We're going to say, well, the current one, right, go to the left. So instead, I think we're going to say, if the current one's left is just a null pointer, so that is, if there's just nothing there, then we're going to want to insert the new node here. Otherwise, we want to move on, right? And same thing here. So if there's no such thing as a right, then I want to insert here. So insert here. And otherwise, what we want to do is we want to make current equal to that. So I think that eliminates a lot of the code to the duplication and stuff like that. And what does it mean to insert something there? Well, it's simply the fact of saying I need to create a new node, right? Sort of node t asterisk new node. That's going to be equal to a new node precisely of type t. It's going to be little guy, and his value is going to be val. I think we can just add it over here, right? So that we can keep track of it. And its color, I think it should be red because that's the invariant. Everything we insert should be red, right? So now what we do is if there is no left, the thing we're going to do is we simply link the current node. So now we need to get rid of previous because we don't need it anymore. That's great. Oh, shoot. I deleted the entire line. We link the current node with the new node, and we already know that the new node should be the left child because the comparator said that like it's smaller than it, so it's very true. And then over here, we're going to run the same logic by linking the current node with the new node, and then it's going to be false, right? Because we want it to be the right child. Remember the link has this function signature that we created a while ago, where it accepts the new parent, sort of the parent we want, with the to-be child, and then it accepts whether we want it to be the left child or the right child. So true for left, false for right. And great, once that's sort of finished, we will know that we want to move on. So this is not only an if, but this is also an indication that we must break out of the cycle. So this else is no longer needed, and same thing over here. So we can just break out of it. So from what we have right now, things are looking pretty good, I would say. Does anyone oppose to this? Because I currently feel really bad. There's a lot of indentation for absolutely no reason. Like Why is there so much indentation? I honestly hate that. So let's see. Can we get rid of some indentation? Well, the currents. I mean, this should be just a while true, right? But I think there's just no way to avoid this. We can have recursion, right? But I feel it's better if we just do it through a loop. The current should always begin as the root. That's one thing. What else? Navigate down the tree till you find the insertion spot. Great, awesome. And then what else do we need? I think that's kind of it, right? I want to say awesome. So if, yeah, I think this is just the, oh shoot. Yeah, I think this is just the insertion part, like all of this. Oh shoot, no. All of, whoa. All of, wait, what's going on? What? I cannot select stuff with my cursor. Okay. I guess all of this is already the insertion stuff, and this is sort of the damage control. No, trying to make it so that we don't break the properties of the thing. If the root is equal to null pointer, then we know that the root is equal to new node. Right. And I guess ooh, yeah. This is a bit of a problem, tiny bit of a problem, and it's the fact that the root is going to start at a null pointer. So we're going to have to include sort of a special case here. If the tree is empty, we're going to have to say something like, well, if the root is a null pointer, then this is sort of k0, right? The root would just be equal to the new node, right? And not only that, but we need the root's color to be black. Color to its dot black. And then we need to return allocator. All right. Yeah. Okay. Now k0 makes it so that the new node is a root. Then make it black. Okay. I am. Okay. So if the root is the same as the new node, then we know that we have to make the new node just change its color. For new viewers, what we're doing right now is we're creating a red-black tweet to use in a memory allocator to get familiar with all the concepts and stuff. So yeah, so that would be case 0. Now case 1 is when Z's uncle is red. That is, the new node's uncle is red. So that the uncle of the new node has its color red. And there's something I am now realizing that is kind of bad. And it's the fact that nils, like the leaves of the tree, the null pointers, they all are of black color. But we cannot access their color property. Right? So what that means is we cannot really directly access the color of an uncle because that would be sort of a null pointer dereference sometimes. So instead, I think we're gonna have to have some sort of function that allows us to extract the color of a node, and that sort of corresponds to how we've been data access. How we've been thinking about most of this stuff, especially with the helpers. So I think color returns just an enum color, and it accepts a node t asterisk node, and then it just simply returns, well, if that node is a null pointer, then it's going to return black as its color. Otherwise, it simply returns that node's color. And we can simplify this to make it a little bit more readable. If the node is equal to a null pointer, then just make it black. Instead of make it black. Black. Otherwise, access the node's color. Great. One thing is for certain though. Yeah, we don't need that space. So awesome. Let's see. Left rotate, yeah, we've already been through this. Attributes, yes. There you go, one call. So wherever we access color, we just need to change the name of that. So color should be something that is not accessed, and thus I'm gonna accompany it by sort of a little underscore to indicate that like this shouldn't be. I'm just gonna look for all of the guys that have color and then a little arrow, and then just modify that for, well, actually, in this case, I want it to be this color. The next case, this is also, okay, because we have a problem. We could make color just return some sort of reference, right? The problem is that this guy is not a reference. So it's just going to go out of scope. It's destroyed in the stack. And then when we try to work with it, it's going to be a mess. I am not sure if C++, if this is even valid in C++, sort of like, is it defined as undefined behavior as of a compile time error? Let's gamble it away and assume that it's a runtime error, that in the case you ever get to work with a reference and it just so happened to return black, then you're done for. And for now, just so that we can institutionalize this sort of use of color as a function, we can use color also to set the color of the root, right? And the color of all this stuff. So the next one would be this guy, right? The new node color. We don't want that. We want the color of new node to be precisely, yeah, black. And the next one we see is, yeah, in the color function itself. So I think that's allowed access. Here, I think we're fine. Great. Okay, so let's continue. If Z's uncle is right, so if the color of the uncle of new node, so new node's uncle is red, then what we want to do is Michael Samuel tells us recolor. I'm not sure what it means. Like in what situation we should?
For this situation, we recolor Z's parent, grandparent, and uncle.
Okay, so recolor. So that would mean change the color of the parent, the uncle, and the grandparent to follow this sort of sequence, right? The parent and uncle black, and the grandparent red. Sort of like we're transmitting down the black color. So we need to recolor, and that means grandpa. We're gonna grab the grandpa of the new node, and we're gonna change its color. Sorry, the color of the grandpa. It's gonna be equal to red. The color of the uncle of new node, it's gonna be equal to black. And then the color of the new node's parent, it's gonna be equal to also black. I am very surprised by how well so these functions interact. Now, the color of the uncle is equal to black. I feel that means we have sort of decided well so far. I feel like when code starts to look like a little bit beautiful, it's a good indication that we're doing things right. We will see. Only time can tell.
Grandparent, and uncle. You might be wondering why B is red, the root of the tree. Just note that this is a subtree. You'll see case 1 is part of a larger tree in the example video. Case 2 is when Z's...
We need to also remember that after we make a transformation, right?
uncle.
So like here, right? In that example, after we make the transformation, which is we change their colors, we need to go up the tree trying to modify sort of the stuff that we have screwed up in. So sort of backtrace on hierarchy and solve errors upwards. Right? Because we cannot just say, oh, case 0, case 1, and then we're done. No. When we perform a transformation, it's very possible that we mess up something else. So we just have to do this, have that as a to-do. Let's see what case 2 is. Maybe we can find out one.
From a triangle.
Okay. Case 2 is when Z's uncle... Ooh. Oh my god. When Z's uncle is black and it forms a triangle. Like Z forms a triangle. It seems like a weird case. So red black tree. Okay. So let's do this. Let's simply say case 2. Well, I'll just say uncle is black, and new node forms a triangle with its grandparent, with its grandpa. Yeah. So if the color of the uncle is of new node is black, then there's something else that we have to do here, which would be and it forms a triangle. So I'm just gonna leave it here in comments, and sort of forms a triangle, which we have yet to determine how to even determine that in the first place. But suppose we know that already, right? Oof. Let me think. Okay, all of these cases actually have a sort of problem if the two things collide. But if we know that the current sort of node in its color is black, then we need not worry about anything. And to fix this, it's backtracing non-return. So we cannot just return over here because maybe, well, actually, no, we can. What am I talking about? Yeah, seems pretty good. So case 2, the uncle is black and the new node forms a triangle with its grandpa. Whenever we have that case, what we need to do is, tell us, Michael.
This is because Z is a left child and his parent A is a right child.
Okay.
You might also see the child.
Yes,
In this
yes.
case, we rotate Z's parent, doing so in the opposite direction of Z.
Okay, perfect. So what that means is that not only do we need to know if it's a triangle, bool is triangle, right? Like we cannot only use a bool for that. We would need some sort of char because, or like character, some sort of number, right, integer, because we also need to know the direction. So it's either right or left triangle or no triangle at all. Triangle, right? So what that means is, suppose we have sort of this variable, right? Triangle direction, treat it. And what we're going to do is we simply say, well, just rotate in that direction, right? So if tree there is smaller than 0, so that would be a left triangle, then it means that we perform a rotation contrary to what Z is in. So that should be a rotate right rotate of the new node's parent. Right, we simply rotate right. In the other case, else, we are simply going to left rotate. Left rotate. Well, actually, no. This one is the left rotate because tridier means it's a left triangle. So we would need to left rotate, yeah. And then we need to right rotate in the other case. So we right rotate the new node with its parent. All right, perfect. Uncle's black, So then we sort of need to know, sort of check if triangle. Right, we need to check if it's in a triangle, our new node. So that's another helper. Not only do we need family members, data access, but we also need helpers that are there for the sake of shape. So whenever we pass to this a node, so check if triangle, whenever we pass to this a node, we pass it a pointer to that node, we're just going to return, well, return a couple of things. First, does your node have a parent? And does your node have a grandparent of node? And also, is it true that you are your parent's left child? So, so here, check it triangle. So if either of this is not true, Then we're going to return false, right? Check if triangle, if it's a triangle, then we're going to just return 0. Otherwise, what we're going to do is we're going to say, well, if your nodes, if the parent has you as its left child, just like what we're seeing here, or as its right child, then at end the node's parent, so the grandpa of my node, has the other guy as its left child, then we know that this is a left triangle. Otherwise, if the node's parent has me as its left child, and the grandpa has him as its right child, then that means that we are in a right triangle. Perfect. Otherwise, we return 0. Because then it means it's a line. Awesome. So now we check if it's a triangle. Great. So now we have checked if it's a triangle. We left rotate, we right rotate. Where are we? We're over here. Great. Check if it's a triangle. Triangle direction. And forms a triangle. So forms a triangle is simply triangle direction is different from 0. Great. Then we want to do this. Right. If it's less than 0, we need to left rotate. It's a left triangle. And if it's a right triangle, then we need to right rotate. Awesome. Otherwise, so that's another thing, right? If the uncle is red, and to do sort of backtrace to fix errors. Same thing would happen here, right? We have an else. And inside of this else, it means that we are not a triangle. So you'll sort of return and then same. To do backtrace to fix errors. What happens is that in this case 3, we have that the uncle is black, yes, right? And by the way, I don't think we need to check for this because we already have the other, this guy, right? Checking for like color red. So if it's not red, then we know it's black already. So uncle is black and new node forms a line with its grandparent. Right? In that case, we also need to know the line direction. So in order to know the line direction, we hopefully will have a sort of check if line function. And we're going to have a new node over here. We're going to pass to it. And hopefully once we create this, it's going to behave exactly like check if triangle, right? Which means that now we can simply say, well, if the direction of our line is less than 0, which would mean left, then we need to do something. Otherwise, we need to do something else. What is that something? Let's watch the video. Let's see.
So Z takes the place of A. Was black, with line as the identifier. Again, C is Z's uncle, but as you can see, Z's parent, and Z's grandparent form a line.
Mm-hmm.
That's because Z is a right child, and so is his parent, A.
Mm-hmm.
The symmetrical situation is when they are both left children. For case 3, we rotate Z's grandparent, again in the opposite direction of Z.
Okay, so that simply means that if we have a left line, then that should correspond to Yeah, left from my perspective, like left. If we have a left line, then we need to rotate the grandpa to the right. So we need to rotate the grandpa of our new node. And otherwise, we need to left rotate the grandpa of our new node. Great. Yeah, feel that checks out. Those are all the cases. So here I also need to add the to-do, backtrace to fix errors. And we now need to create the shape helper to detect when a line occurs. So type in T, and then we're going to have a chart check with line. Check if line is there. So I'm going to have a node. I'm going to point it to that node. And first thing is that we need to have a parent, and we also need to have a grandpa. If we don't have either of those two, there's no way we can check for a line, and so we simply say nothing. Right? So that's another thing. We need to, just for the sake of our own sanity, I'm going to assert that this thing is just not zero. That is, we know that we are a line. If at some point in time that happens to not be aligned, then we're in trouble. Big trouble. So what we're going to do is we're going to say, well, right, check that. So first let's do the left line, which would mean my parents' left child is myself, and my grandpa's left child is my parent, right? In that case, I know that I'm a left line, so I'm going to return -1, left. In the other case, where I have that my parent, so a right line would be my parent has me as its right child, and my grandpa node has me as a right child. So the right child of my grandpa, sorry, is my parent, right? My parent is the right child of my grandpa, in which case I return 1, right? I think it's the exact same code, which is great. Otherwise, we return 0 saying, no, sir, I don't know what you gave me. This is not a line, right? So that is check if line. And there you go. We have it. So that's case 3. And I think those are all the cases, right?
So that A takes the place of B. For case 3, you will need to recolor the original parent and grandparent after the rotation.
Ooh. Okay. That's new. Oh wait, this is violating the...
After the rotation.
Okay, guys, we're going to have a huge problem here. Because after this rotation occurs, we now have a violation of the red-black tree property, because this guy, right, there's 2 blacks on the way to the leaves, while there's only 1 black this way, which means that we will need to check for errors somewhere other than our ascendants. And that is bad, because it means that we cannot backtrace the errors. That's okay. Okay, but other than that, we also need to apparently recolor, right? So with recolor, I imagine that he means, well, this would have to happen before the rotations, because the rotation change all of the relationships between nodes, like a lot, since it's going to rotate the tree. And like Z's parent, yes, was A, and A's parent was B, but now after the transformation, A has no parent, so Z has no grandpa. So we need to perform the coloring beforehand. And so what we're going to do is we're simply going to say, well, the color of the grandpa is going to be, is going to end up being an equal to us. So that means that it also has to be red. And it means that the color of our parent, new node parent, right, it has to also be, it has to be black. Black. Great. And then after that, our color is still red, and then we continue. Awesome. Okay, I think we have it. I think we have all of the cases. The only problem that we're going to have, or like not only problem, but a very bad problem that we're going to have is precisely what I mentioned, that we're going to need to backtrace in order to fix errors.
That's it. Let's review quickly. To start, we insert the node and color it red. Red-black trees have certain standards, so we must recolor and rotate nodes to fix violations. There are 4 possible fixes we'll encounter. First, when Z is the root, we color it black, grandparent and uncle. We rotate Z's parent. And when Z's uncle is black and a line is formed, we rotate Z's grandparent and do some recoloring.
Okay, no, that makes sense.
Here's the pseudocode.
No. Okay. Don't show me the pseudocode, please. We need to perform now the example for the insertions. That's over here. So let's see.
Today, you'll see examples of red-black tree insertions.
So
definitely
the reason
with my
why
red-black tree videos before you watch this one. Remember from
Michael, stop. Okay. The reason why we sort of need an example is precisely because we've been coding this red and black tree class. We're going to use it on a memory allocator in order to find the best fit block for given requests. So the thing is, we're coding insertions, right? We have everything, we have the cases. The only problem is that whenever we perform an insertion, it's possible, it seems to me, that there's going to be we're going to need to backtrace to fix errors, right? Because any sort of transformation that we perform is going to modify something else in the tree that potentially breaks the rules of a red-black tree. And the ideal scenario would be that those errors only happen upwards in the tree, sort of in your ascendance in the tree. Problem is, I think there could be situations where the errors do not happen in your ascendance, but below, which means that you would have to check the entire tree in the case errors were inserted. So we're going to go through an example to see if there's ever a scenario where that happens. That is, where there's an error that appears not in our ascendance. So great. Oh my god, wait. There's somebody here. It's Arctic Codes. Arctic Codes. Thank you for following. I mean, you're my second follower. This is great. Yeah, I just started, yo, hello. Just started on Twitch yesterday. As I was mentioning, we're coding a memory allocator. For now, we're in a little bit of a boring part, which is we're creating like a red-black tree from scratch. You may be asking, like, why not just grab some sort of implementation of a red-black tree already out on the internet? And it's the same answer for the memory allocator, right? Why are we writing a memory allocator from scratch in C++ if malloc already exists and jmalloc already exists? We're just doing it for the sake of learning. So, I mean, we're just trying to learn, and I really want this to be from scratch. So we're creating the red-black tree now. I do have to admit, it's like a little bit of the boring part compared to creating the memory allocator, but it's definitely needed. So yeah. Oh, thank you. But yeah, hopefully it'll work. And let me These things are da. All right, you can stick around however long you want, and yeah, we will continue with what I was mentioning. And also, if you have any ideas, like please take a look at the code. If you disagree with something, it's like completely tell me. I'm a college student, and I'm learning sort of more low. I love low level programming and all of that stuff, but I don't have as much expertise, so it's possible I make a lot of mistakes. Let's see. I don't write C++ as much anymore, but I might in the future. Oh, that's great. But yeah, I mean, what what do you write on? I mean, if you don't mind me asking, like I think I don't know. People use a lot of languages. I've been very happy with C++ for some reason. It's like very low level and stuff like that. I feel like I would embark on Rust too to see and Go like oh that makes a lot of sense. Okay. Um, Go is also nice too. I feel Go is very sort of simple and it's a very yeah it's too simple and I feel that that's what makes it or what gives it the advantage that everything is very explicit whenever you want it to be there. Well, that's great. Um, yeah, no, exactly. Yeah, I mean simple, not in the sense of the learning curve, but like everything is really explicit. I think explicit should have been the word I should have used. Where you every single statement is like if error nil, no. So it's I don't know. I feel like I let go. I would have to try a little bit more of it. It seems like you seem to enjoy it a lot. So yeah, it is definitely sophisticated. But yeah, let's go. Woohoo. I'm trying to see if I can surf through the example to try and find if there's a situation where something weird happens. Let's see.
Let's do another one. This time 5.
Okay.
Let's try in a row.
Okay, we have the first conflict, which is there are two reds together.
Z
This
is
a
1,
line.
the node we just inserted. Its uncle is 15's right child, which happens to be nil, a black node.
Mm-hmm.
This is parent and Z's grandparent.
Okay, I think we understand the rules from what we've been coding so far, so I'm going to skip and try and find somewhere where what I was describing happens. So far, so an example, right? Whenever we create the fix for this by rotating the tree, we end up with another conflict, right? And the conflict is that the rules say that the root and the leaves are always black, but after the modification, the root is no longer black. So now we have to fix that. Fortunately, it's an error that happens above us, right? To like the nodes above us, so we can simply like backtrace. I'm trying to find a situation where it doesn't happen in the nodes above us, but instead in like some sort of sibling or something similar, or like a child. Oh my god, what is this tree? Oh my god. Let's see. We have 10. Oh wait, another message in chat. I like it for the simplicity and compile times. C++ can get really crazy, but obviously C++ compilers do optimize much better. But the thing with me is that I prefer to manually optimize anyway. The issue is the header files in C++. Yeah, I can definitely see that. I think C++, especially when like, it's like very easy to get introduced into template hell in C++ from what I've seen. I don't have much experience with templates though, but like the little stuff that I have other people sort of code is extremely crazy. It's also good that Golang is sort of doc typed, where I don't know, it allows for more versatility. I feel it's like one of the good features of the language, and prefer to manually optimize anyway. That's good. This is really good. I feel like manual optimization is like way better. Go type in for okay, yeah. And header files in C++, yeah, they are a little bit annoying. I do have to agree on that. it's really, I don't know. I I I mean, in this case, I'm writing the code in the header file itself. It's just because like the separation is kind of a little bit annoying sometimes. Um, but in this case, it's because we're using templates and C++ forces you to write them in the header. Um, but yeah, I feel like every language has like its pros and cons. And I don't know. I like the fact that C++ feels very low level and there's like a lot of stuff you can do. That comes with its trade-offs though. And I think the same for other language. Let's see. It's like C++ auto. And by the way, I don't hate C++. I know. I didn't assume you hated C++. Like you mentioned that you coded in C++ for like a long time. So I assumed that like, coding C++ for a while, like if you hated it, you would have ended that journey a little bit earlier. I hate more of everything surrounding language, like the STL, CRT, runtime, and just Windows header files. Yes, that is true. And the STL is like, yeah, the STL is a hot topic in the C++ community, especially when you have like things that are really not optimized to maybe your use case. I feel like it connects back to what you said about sort of manually optimizing stuff. Um, Maybe not going to the extreme where you would have to optimize every single data structure that you use from the STL. But there are examples, right? Like an order map. I think the C++ implementation of an ordered map is the same one that has existed since like 1998 or something like that, which is kind of insane. And I feel okay. It all connects back to Go. God, I'm not trying to praise Go because there are some things about Go that I don't like. But one thing that can be said is their hash tables excellent. I think correct me if I'm wrong, but I think Go uses the Swiss table that the Google engineers created. I don't remember. I remember there's a CPP conference about this, about the Swiss table being introduced. I don't remember the name of the presenter or the creators, but yeah, slices are built in. Yeah, slices. Like, yeah, there's a lot of stuff. I feel like if it comes to a standard library, definitely Go has the advantage. Uh, C++ like it is decent, but I feel like the example of the unordered maps already illustrates a lot of stuff that like it would be better if it changed. I guess like the solution to that is like using external libraries like Boost, right? Um, Boost is supposed to be sort of a replacement for the STL where everything is a little bit more optimized. But even then, I feel like there are certain constraints that the language imposes that, especially in the case of unordered map, like unordered map and Swiss tables, like the consequence I think of Swiss tables is that you cannot really store pointers to like the objects you store in your map, or like you cannot keep a reference to the object that's stored in your map per se, which is one of the things I don't like about working with maps on Go. I guess you get used to it as you use them. Like I'm not sure. You should let me know. But it is you can use pointers for sure. Yes, but like um, if when your map stores like you cannot really do something like if I were to I don't know something like here in the main function if I were to do something like like some sort of map, right? And then I just say like auto sort of value inside map, and then make it just be this, like map at 45, yeah, access some sort of element, and then change that element, or something like that. Dot color equals I don't know equals red, right? Like this sort of thing. If I remember correctly, you like this cannot really be changed. You have to sort of reinsert the element. So you cannot keep like a reference to the things that are inside your map. I think that's a consequence of how the Swiss table works. It's like one of the contracts that it breaks. And the problem is that the C++, the C++, what's the name? Sort of language specification prohibits any sort of implementation of a map that doesn't allow you to to store a reference to the value. So like the language itself imposes some constraints that just would never allow, say, the Swiss table to be the new standard unordered map, which I guess it's fine since like so many programs have already been used to being able to store a reference to the values and stuff, that if you were to introduce that change, it would be like absolutely catastrophic. But it is still a restriction nonetheless. So that's like a little bit a little bit a little bit of a like I wish it has a different. I didn't have this problem yet. Oh, okay. That's great. You're lucky. I remember I was coding. What was it? I think it was a distributed database, like not a serious distributed database, but like a sort of toy example with like shards and stuff like that, and you really need maps for that, and that's where you start encountering this sort of stuff where you're like, "Ugh, I don't know if I would, I don't know if I like it. But yeah, it's cool. You know, it's a good language. I feel C++ is also a good language. I personally like C++ more than Go. Maybe that changes in the future. Uh, Not sure about that because I'm really currently in love with C++. Once that goes away, I'm gonna be like a little bit more objective, like on looking at these problems. Um, so yeah, it definitely depends on you. I think if it is well, yeah, yeah, completely agree. C++ more low level. I feel Go can also be used for low level, but it's definitely better in other fields. And yeah, every language has its own use case. Rust is an example for also systems programming. But yeah, I don't know. I'll continue. Let's see. So we recall it this. Okay, when we have this, we have the problem between 9 and 10, and then we recall it, as the rules say, but now the problem has been inserted here. But that's an ascendant, so that's good. And then we change it again. Oh, what the hell was the transformation? Okay. Ooh, okay. So whenever we make the fix, which is this one right here, the problem transfers not to an ascendant, but to a sibling right here, or like to something that's not in the same level. But I guess it's still the parent, right? Like 15 is the one that generates the problem. So I guess it's fine. Okay, we fixed it. Then when we try and fix it again. Oh no, don't show me the pseudocode. Okay. We will have to think about this more mathematically to sort of prove that the failures are only going to occur between the ascendants. So I don't know. Oh wait, no message in chat. Because I am writing applications that have to be cross-compiled and use a ton of encryption and make network calls, and all of that is built in. Yeah. No, that makes a lot of sense. But dude, this sounds like extreme engineering, cross-compiled application with a ton of encryption and, and a bunch of network calls. Working for the NASA, it seems. It seems like a a, a very involved sort of project that you would be coding. But I definitely agree. Go seems like the perfect language for that. I don't know. I think Go has even a feature where you put a whole folder in an embed.fs and then just what? What? I did not know this. Is that really? Damn. Dude, what are... Okay. That is kind of crazy. I feel that that is the sort of feature that they would ask you to implement yourself. Let's see, open link. Let me copy it here. Package.go/embed. Okay, we're taking a detour because I do want to take a look at this. Provides access to files embedded in the running Go program. Go source file that import embed can use the go embed directive to initialize a variable of type string. Example, here are 3 ways to embed a file and implement the txt and then print it onto the runtime. Okay, we imported go embed, embedded one file into a slice of bytes, embedded one or more files into a file system. If the read file, dude, this is crazy. Directives specify which files to embed using one or more math patch patterns. Yeah. Go build system will recognize the directives and arrange for the declare variable to be populated with the matching files. Wow. This is okay. Now I am sort of confused on how you come across this sort of stuff, or like, what were you doing that you needed to find an embed package to embed the entire file system? But this is very cool. Yeah. Damn. Oh wait, AirPods are about to die. This is my only microphone, so I need to keep them. Let me see. Okay, I'll try this again. The command tells the compiler to do the folder. Yeah. Mentioned in the documentation. Ooh, okay, that is a good use case. Self-contained HTTP server. Yeah, pretty good. I guess, yeah. I guess I have like not much authority to talk about Go because I've never really done like a serious sort of coding when it comes to Go. Only like very small projects and stuff. Go generate extra files when you use UI to import audio fonts. Yeah, all of these make sense. I feel that it's also a problem that definitely happens. You can generate bindings to Z automatically. I had heard of that. Like some people, like I've definitely seen it Go to be the one that is usually used for cross compile, or for like interaction between different programs. But yeah, this is pretty good. And I don't know. I know what other languages. Yeah. I've heard Zig has similar stuff when it comes to compatibility with C. I'm not an expert though. Would have to look into that. RE stuff and evading security systems. Wait. What is RE? RE. Let's see what. Evading security systems is pretty clear to me. But what is RE? Polymorphic code, etc. Okay, I see. Evading security systems. Some sort of white hat hacker? Like this is kind of insane. Then means you. Oh, reverse engineering. Okay. Yeah. That makes sense. Damn, yeah. So then you're like the exact type of person that's like interested in the low level side of things. Yeah, I feel like it takes a specific type of programmer to click on a coding a memory allocator from scratch. But yeah, no, I'm happy. Pretty good for you. So I imagine you're an expert on memory on memory in general. No, I feel like it's like the world seems interesting. Never really delved into it. The only thing I'm aware of is that basically all of the vulnerabilities in the case of operating systems have been ultimately happening within the realm of like memory and overflows, etc. I was interested in RB trees before because I was working on game engines before. Dude, who are you? Like, what? Game engines? You've been like, yeah, incarnation of the 10x engineer. I see, I see. That's interesting. Because yesterday, another of our viewers was also into the security world. He was not very familiar with red black trees. But and so like none of us knew about red black trees, so we were trying to learn about it. And right now, at the beginning of the stream, we basically had just the structure for the class of the red black tree and nothing else. All of the day of today has been spent on writing the red and black tree class and all of that stuff. So glad you've known about red black trees. So this is gonna be like a, a really boring part. Also, if you have like if you maybe like are we guaranteed sort of mathematically this thing that errors will always expand upwards? But I don't know. I feel it's like a very weird question to ask. But if you ever know the answer, let me know. Because right now, that's what we're going to start analyzing. And let's see. Also host your own Git server. Oh, that's pretty cool. Yeah. I That's actually a pretty good idea. I feel like hosting your own Git server. That's pretty. I feel like it's like it, it is weird. It is strange because it is something I have noticed with like other programmers I have seen and interacted with, and it's that it seems like the more experience sort of you start accumulating, or the more things you go through, the less confidence there is in sort of like external dependencies, or more motivation you have to do your own stuff. You want to have a GUI, etc. Oh, you have it with a GUI and everything. Damn, that's pretty good. But yeah, it seems like experience is directly correlated to to being like a little bit skeptical, and I guess it makes sense. Skeptical in two senses, in the sense that, I mean, when it comes to corporations, right? Like currently looking up the uptime of GitHub is like a little roller coaster, absolutely insane. So in the specific case of a Git server, maybe that could be a motivation. But I feel there's also the part where once you have enough experience and you know how all of the parts move, there is a motivation to say like, okay, I know that this can be improved. Like I know for a fact that things would be better if I were to do them myself. So I think it's interesting on that side. Like everyone starts doing like their own, like, their own version of things, in sort of this skeptical correlation between experience and creating your own stuff. But yeah, I don't know. It's interesting. I don't know. Well, I'll start drawing here some, thinking about whether or not things propagate upwards. I think a way in which we can tell is we can go back to the strategy cases.
Today we're going to learn about red-black tree insertion.
Thank you, Michael. Here. we have just like a list of what happens in each case. No. Show me the pseudocode. Oh, my Wi-Fi seems to be slow now. There you go. Okay, well, that's part of why I chose Go too, because it has such an extensive standard library that's well written and tested. Yeah, that makes a lot of sense. It's pretty good language. I feel like the fact that it was a modern language, they definitely kept up with their philosophy. I do know there has been a little bit of a controversy. I don't remember with what. I think it was they were introducing something new to the Golang type system. But all I can remember is just a fuzzy cloud, right? Where I'm not sure if it was templates, but templates. No, I think yeah. I don't really remember. I do remember there was a division in the Go community where, where people were saying like, no, this shouldn't be introduced to a language. And others was like, yes, this is perfect for Go. They have tried to stick to their philosophy. And when there's like a minor deviation from that philosophy, just like it happened with whatever I'm mentioning, which I cannot really recall, the like everyone starts to get angry or discuss, which means they've done a good job. You know? They've created like a system that obeys that design philosophy. In C++, I had to use Boost for sockets, UDP, and HTTP, and other libstructure. Yeah, exactly. I feel like most of the C++ stuff you need to vendor in. Go, yeah, has it extended enough that all you need is basically there. Not in the sense that like all you need is there and so it's gonna be like super easy, but like there's some basic stuff that you should have, right? I feel like the best example is yeah, in the case of cryptography or hashes and etc. I think C++ has no native implementation of MD5, which I know it's like not too cryptographically secure, etc., but it's good for hashes. You need to import it from OpenSSL, if I remember correctly. So now you need to vendor in OpenSSL, and stuff like that. Stuff that seems rather basic when it comes to programming. So yeah, but in Go it's all built in and works great. And if you have a website also written in Go, it's the same on both sides. Yeah, client and server. Yeah, no, that makes total sense. I don't know. I feel like I would have to explain Go. Not explain, sort of explore Go a little bit more. Is there anything you would recommend to like I personally like sort of learning new things and like concepts in programming languages through projects, because then it's like, I don't know, it's like code this thing and then you have absolutely no idea, so you sort of throw yourself into the void, and then you know that you have to find a way to get out of it. And then when that happens, it's the time you have learned. But is there some sort of project that you think like, oh, doing this in Go will be like, it will introduce you to Go. It is good when it comes to interacting with the language, and stuff like that. I don't know if you have some suggestion. Meanwhile, in the meantime, I'm gonna be here like just writing stuff, trying to figure this out. Let's see, when the root is black, we are fine. Fine. We've reached the top. Let's see. So 1, no errors propagate, that everything's fine. With 2, c.uncle equals red. Then we have in the case that z.uncle equals red, we have to recolor. The way we recolor it, by definition, expands up or extends upwards. In 3, z.uncle being a black triangle, and in this case we rotate the parent. So the parent is red. And when we rotate, the problem manifests itself. Well, if we rotate the parent, then it's a triangle. If it's a triangle, okay. Well, if it's a triangle, we have a problem. Oh wait, another message. I would say something like a game would be fun, or a chat app. Okay, that seems decent enough. I have never really coded a game. Like I feel it's like one of the projects that many people have done. I've absolutely no idea, never done something like it. A chat app seems like simple enough that I feel could work. Because I have to say that my introduction to Go was very. It was it was kind of painful. Like it's kind of the reason why I I sometimes don't like Go. And it's because, as I mentioned, my introduction to Go was implementing, like, I think it was implemented a primary backup sort of system, right? And after that, implementing Paxos from scratch. And it was a nightmare. Like it was so first of all, you have like, you need to create your own, so the server, right? The Paxos server, or like a Paxos instance, or like little machine, a Paxos member, right? And so you receive all these RPC calls, and you have to keep track of the state. And if you receive another RPC call, it just so happens that like Go is not non-blocking. Instead, it creates another Go routine for the new RPC call. So now you suddenly have two threads, although Go routines are not necessarily threads, but thinking about it as threads. So now you have two threads. And so now you have two threads trying to modify the same state. So then we go back to sort of async management and all that stuff. So since that was my introduction to Go, it was like I ended up like not liking Go at all. And since it was so explicit, like you had to sort of manage every single error and be like, it became really annoying for me. But I think that is not Go's fault. I think that if you're introduced to a language and the first thing you need to do is implement Paxos from scratch, it's like you're shooting yourself in the foot, and like no wonder why you're gonna hate the language. Fortunately, that was not the case for C++ with me, but that's why I'm asking for sort of a project that could be good for Go, because I have been introduced to the language, which is why I sort of know kind of what Go is and how it works. Definitely not an expert, but having something to appreciate the language and be like, yay, this is like very, very cool. Yeah, it is. Okay, yeah, no, that makes sense. So a chat app, for example, would make a lot of sense. Yeah, I would have to take a look at that. I feel like I have some. That is a good contender on what to do after we finish the memory allocator. Because yeah, I don't know. We'll see. But let's see. You can build a self-contained tool that's just an exe and has a web interface for controlling it. That seems really cool. I feel well. I imagine that's where the embed package comes into play. But yeah, so then it makes sense. It's a natural connection. But yeah, templating is built in. And yeah, I don't know. It's yeah, definitely. It was not my wisest choice to start and go with Paxos. But it is what it is. Things happen, and we all make poor decisions. Oh, what the hell? Z is parent changes. Huh. See, if A had another child. Okay, I see. Yeah, using third party lives in the I feel that is a great thing to be able to say about your language, where things are like optimized enough where you don't really need it, and everything is self-contained to the point that you're like, why would I need something extra? Yeah, it's pretty good. Trying to think of this case. Oh my god, it's ZM! ZM is coming back. Tim, what? ZM, for those who don't know, is the person that was in our lab in the stream from yesterday, where we were starting with. It was our first day with the memory allocator. That's why the title says second day on Twitch. And yeah, ZM, welcome back. All we know about Go is it has generics, which is a weird thing to omit from the language. Yeah, and yeah, exactly. Okay, that was the controversy. The implementation of generics in Go. Arctic and I were talking about like Go's sort of design philosophy, and sort of the fact that they have stayed very loyal to their design philosophy. But recently, a change was proposed by sort of the Go committee, or like the ones in charge of the language, where generics would be introduced to the language, and this created like a huge division because it's part of sort of Go's philosophy. It seems that generics should not really take a place in the language, and divided the community like into one that it was like generics are very useful and like they simplify code a lot, and others that said yes, they're very useful and simplify code a lot, but this goes against the sort of philosophy of simplicity that Go has acquired. And I don't know, but I couldn't remember exactly what the controversy was, but yes, it was generics, that they're introducing generics now. But yeah, I don't know, it's interesting. Well, actually, it has generics which were just empty and interface, but they sort of yeah, exactly. The formal introduction of generics was the problem. Yeah, I don't know. Here we are. I mean, I was ZM. I was mentioning to Arctic that it is a bit unfair. I don't really like Go that much, but it was because my introduction to Go was creating Paxos from scratch, and that being the introduction to anyone for our language is really bad. So no wonder why, and I don't know. I'll give a shot to Go again eventually. How do you implement a container type with no generics? This is a great question. I'm not sure. Maybe Arctic, you have more experience with Go. Is that like a problem you encounter, like implementing a container type interface? Oh, so you just okay. So from what I understand, interface brackets is just the equivalent of like any in sort of TypeScript. So you just like, oh, you use pointers to interfaces. Interesting. So does it mean that you cannot really control what goes into your container? Like if I try to create, say, a vector in Go, and then I just say sort of vector.pushback or something, and then I put 5, and then I try to push back a string, both of them suffice the interface bracket since it's an any, but the language wouldn't be able to, at compile time, detect that this is not what is supposed to happen, or like is because I feel like that's where generics would go in. But if Go doesn't have like formal generics, oh, with dot type, okay, so it's a bit of like a funky. Okay, I see. You just switch on dot type, and then when you try to switch it on dot type, it's gonna complain and it's gonna tell you no, this is not a. Okay, I've compiled it. Okay, Okay, I can see. Okay, I can see that happening. Sure. I mean, it seems like a funky way, but I feel it's it's staying loyal to Go's design. Let's see what happens when they implement sort of like the generics more formally when they're have they implemented generics formally now? I just remember the announcement. I don't remember if it was already in the new Go version. Oh, they have them now. Okay. Makes sense. Yeah, we'll have to give Go a shot. We'll see. But yeah, let's keep thinking about this problem with the red and black trees. For those who don't have much of a context, how's the tree coming along? Yeah, we are. So, Zian, just so that you sort of have a context of what we've been doing, we've coded a lot. Like there is, we decided to separate things into this node struct and have the RB tree be just a general sort of landscape view of things. We're currently implementing insertion. The thing is that insertion is sort of the nitty-gritty of red and black trees. Since find is very easy as it is just a binary search, tree search, right? And we've been introducing sort of the left rotations, right rotations. These two are the same as an ABL trees, as we were talking yesterday. I introduced this link function to make it simple to sort of tell two nodes that they're like one is the parent and one is the child. Since we have family members now. we have the grandpa of a node and we have the uncle of a node. We have color because the leaves in a red black tree are considered black. But if you try to do like null pointer and then you try to access its color member, then it's going to be really bad, no pointer to reference. So we have to use color in this case. We have these things called triangles, as you see here in the right. We have these things called like lines. So we also have to deal with those. I don't know, we've been doing a bunch of stuff. And the thing we have right now is the following. So whenever you perform an insertion, right, you have to respect the rules of a red-black tree, which are precisely these rules. There you go. A node is either red or black, the root and leaves the node are black. If a node is red, then it should turn out black. And all paths from a node to its descendants contain the same amount of black nodes. And nils are considered black. So that introduces the why we chose to do the color and whatever. But whenever you insert something, you have scenarios, right? So if you insert the root, you will always, when you insert something new, it's red. So if you insert the first element, it's going to be red, but that violates the first rule that says that the root must be black. And so the solution, we simply color it black, right? Like right here. It gets color black. Another case would be whenever you insert something, the Z, right? You insert it here, but notice that this breaks the rule that says that if a node is red, its children are black. And that's not the case here. Whenever you see two reds colliding, really bad. So we need to fix that. And then that is case one, right? Whenever this happens and your uncle is red, then you have to do something. And that something is you need to recolor, right? You need to change the color of your parent to black and of your uncle to black and your grandpa to red. But notice that introduces another problem. Now we've broken rule one. The root is no longer black. Yeah, exactly. So if the root is no longer black, then you need to now go up the tree and fix the problems that you have introduced with the most recent fix. So even though we fixed the problem that was down here, then we introduced a new problem upwards, right? So it's sort of like once we are here at the bottom, we could sort of recurse back up, and then solve the problem or the problems as we find them. So that would be relatively simple. like maybe question mark, because we just go up the tree, right? And then we're like, all right, is this a conflict? Is this a conflict? Is this a conflict? And we would only have to perform like log n comparisons. So that's completely fine because insertion is already log n. The problem comes, and this is what we're analyzing right now, is I think it's this example, right? Whenever you have a black triangle, or like your uncle is black, and you have a triangle, then you need to rotate the tree. So you need to rotate the parent, right? Like that. But as you can see, that solved the problem there, but now there's a new problem here. So now we need to fix this problem. Because now this is not a triangle, now this is a line, right? A's uncle is black, and it's going to be a line. So that corresponds to case 3, right? So then it becomes like a little bit annoying. And my thing was, okay, sure, we can classify this in cases, which is very nice, which means you only have to check for those 4 cases. The only problem is that this example of case 2 kind of shows that the problems don't necessarily propagate upwards. They could also be propagated to your right or to your children. What I'm saying is, in the case 1, right here, where we introduce this other problem, we know that if we have ever introduced a problem, it's going to be above us. So we can just go back and fix the problems as we go. But if the problems we introduce also happen to be below us or to our right and to our left, then like we literally don't know what could have gone wrong, right? Like it's so what we were thinking about was just like, okay, are the errors localized and to what extent? Sort of like analyzing each case and saying like, okay, we know that an error will be present either on a sibling or on an ascendant, nothing below us. What could introduce an error below us? This rule number 3, is the literal incarnation of the evils of the world. Because it says all paths from a node to its nil descendants contain the same number of black nodes. So you could fix something, and then it just so happens that the path from the root to some random child now has one more black node than it's supposed to. And then like, how do we detect that? Like, I'm not sure. You can see it with your eyes very clearly, but it becomes like a pain after. And that's what we're trying to see, like, is behavior localized? So in the case of a root, whenever you perform a root fix, yes, you're fine. You've reached the top. So there's, you change the color of the root to black. And in that case, nothing happens. No rules are violated. AVL is so much easier. I remember in RB3 you had no. Yes. AVL is so much easier. Yes, it's way easier. It is the price we have to pay for saving a little bit of memory, which is like 25% of our memory usage. So we introduced the parents, and now it's 20% of our memory usage, the difference between an AVL and a red-black tree. So it is definitely something that we need to, it is the hell we have to go through, unfortunately. But yeah, the root case is we reach the top, everything's fine. If your uncle is red, the solution to that is recolor, and that's what we had over here, right? Is recolor. So you color your parent and uncle black and your grandpa red. In that case, the only one that could generate a problem would be your grandpa, right? And your grandpa now colored red, so now you know that error extends upwards, right? So we're fine in that case. In the case that your uncle is black and it's a triangle, we rotate the parent. And this thing happens. it's just extremely weird. I don't know. But okay, would anything below us be affected? Well, if you have any sort of children, we're not recoloring anything. So the third rule, all paths from a node to its nil descendants, it's still fine because we're not recoloring anything. And the root and leaves are always black. That is still fine. Because then if what we happen to rotate is the root, then we simply recolor it. And we already said that case 1 doesn't introduce any sort of upward error. So then the only problem is this one. And it seems like there's no way you can affect anything below this. So I think we're also fine. This extends not upwards, but like it's like problem persists, but with your old parent, right? Because it is technically still extended upwards in the sense that A was the parent. So now, even though now A isn't the parent anymore, we still hold the reference to A as the parent, right? So like we still have access to it and we still know what node it is. So we still know where the error sort of lives in. So I think we're fine in this case. So it doesn't proliferate sort of under us. And in this scenario where your uncle is black and it's a line, then we need to rotate the grandparent. Okay. And we now have a problem here, but that's still upwards, so that's good. Oh, and we need to recolor also, apparently. Okay. So when we recolor, are we somehow breaking the rule that we previously had about the path to a leaf has to have the same amount of black nodes? And the answer I'm willing to say is no, there's no problem because the root was black previously, and in the new tree, the root is still black, which means that everyone is affected by this recoloring in the same way. Like the amount of blacks stays the same no matter what branch you're in. If it were to be kept like this, then yes, for sure, like, right, there would be like 1 nil here, and then it would have 0 blacks on its way, and this one has 2 blacks on its way, so then it would break the rule. But the recoloring takes care of that, it seems. Oh no, wait, never mind. I'm completely lying. Wait, the example itself shows you that this nil right here, the left nil of Z, is black by convention. Every single nil is black. But there's only 1 black in its path compared to the 2 blacks that this one would have. Whoa, what is going on? Oh, okay, no, I think we're saved. We're saved. The example was rigged from the start, right? Like, look how the original state was already an invalid red-black tree. This one has 2 blacks in its way. This one too. This one has 2 blacks in its way, B, and then D. And this one has only 1 black in its way. So we're fine. It's just that the example was like wrongfully constructed from the beginning. And I think the action of rotating the grandparent and then recoloring by what we were saying before doesn't really affect rule 3. So we should be fine. Okay, it seems like we're fine. It seems like we can take as an assumption the fact that errors will propagate either like upwards to our ascendants or to an old parent, right? Like some weird thing like that. Like, I don't know. Problem persists, and in this case it could persist, but actually no, I think case 3 gets rid of the problem completely because it recolors the root to black. So anything that's above it will now have absolutely no conflict. So yeah, this one just solves the problem. Solves the problem altogether, I think. We are not introducing a red in a position that it shouldn't be because the root is now black. So anything that connected to this subtree will have a black child, which is completely fine. The amount of blacks that we had in the path is exactly the same because the root remained black. So we're fine with rule 3. And with rule number 1, the root is always black. It's still preserved because we recolored the root to be black. Okay, so this one, that case solves the problem entirely, and then we know that there are no more problems after this. So, potential optimization? Although, like, really doubt yourself when trying that optimization. We do not want to start optimizing being like, oh yeah, case 4, we can finish early, because we may introduce a bug really easily. And because the reasoning was done in like 30 seconds of me saying, yeah, that sounds about right. Like, so let's not do that. Let's just keep it like this. We know it solves the problem, allegedly, but let's just assume it doesn't, and it propagates the errors upward. Okay. With that in mind, then we need to transfer that thinking to code. And okay, this is gonna be really painful. It's gonna be really boring. So I apologize in advance. Let's shrink this a little bit. Hello? Yeah. So okay. Bear with me while we regret all of the decisions we have made so far. We navigate down the tree until we find the insertion spot. This is the usual algorithm for finding something in a binary search tree. We simply look for the element and then bam, we have it. What we want to do is, there's going to be a to-do. It's like make sure that on a search, let me think. Oof. Okay. I'm starting to see a problem that future us will have to resolve. And that's the fact that in our memory allocator, right? So I think this tree on the right is very good for what problem we may be facing. In our memory allocator, right? Suppose I'm looking for, I don't know, some 12 byte block. So I go here, and this thing happens to be really big, so that I just go to the left, and this happens to be 4 bytes. It's too much. And then I go here, right? Suppose this D didn't exist. So then I would have to insert or like to, well, actually, no, suppose this D does exist. And then I know that this D is too small for me for the request. So then the block that I would need would be on D's right. But that is not the case, right? Like, is there any case in which the actual node we need is the one, it's sort of our uncle instead of this? No, I'm stupid. That's not how binary search trees work. Yeah. So if we ever need something that's greater than D, then it means that we could have been, or we would have been sufficed with taking A. Because D is even greater than A. So okay, no, that makes sense. Sure. So never mind about this. Okay. We find the spot to insert our node. Then after that, and this is the to-do, right? Backtrace on hierarchy and solve errors upwards. Like we we return right now, but no, we need to go up the chain of command. Let's see. So if the color of the node to which we inserted is black, there is no way in which we could have introduced any sort of error. So that means we're fine. If that's what we ended up inserting, then we can definitely return. Now, the new node is the root. We can make it black. This is also fine because it means the tree is empty, so we don't have to go upwards for anything. This is literally the first node. Great. Now, if the new node's uncle is red, then it means that we need to recolor. And when we recolor, we know for a fact that we introduce problems upwards. So now we need to check up. The question is, how do we check up? I feel that if we had recursion, this would have been so much simpler. And yeah, I think that's exactly what we're going to do. Because, okay, so the reason why I mentioned that recursion would have been really helpful is because we can simply sort of, instead of doing this whole trip, we can just call like insert, and then we pass in sort of the same value, but now to our left child or right child or whatever. And then when they return, we simply say, okay, suppose that the one we inserted was my left child, because I know that the problems can only come from my left child. And then I can just run these cases again and simply return when I'm ready. And then the calls of the stack are going to think the same thing, and the problem is going to be solved recursively. The problem is that not every node is a red-black tree, so we cannot treat we cannot treat subtrees as red-black trees. So some of these cases don't apply to subtrees. So I don't know. We could perhaps simply keep track of the nodes we have traversed through a stack and just call it a day. This may just be the thing we do, because honestly, it seems like the only reasonable solution. Yeah. Okay. I think I'm a little bit blocked. Don't really know how to proceed. Okay. Let's think for 2 minutes. 2 minutes of silence. Or at 6:16 PST time, we're going to resume. But for now, we'll be silent and let's think about this. The parent and new node. The root is in the new node. Oh, wait. Boss Dance followed you. Yo! We have a new follower, guys. Our third follower. This is great. Hello. Thank you for landing in the stream. We're solving this problem with the red-black tree that I hope you've been looking at. It's been 4 hours of looking at red-black trees. So, I don't know. But yeah, let's dedicate a moment of silence to thinking about this. Let's see. Red-black tree. Okay. Okay. I think we have a game plan. I think I have a game plan. 6:16 as promised. Only 6 minutes. 6 minutes. Whoa. It's 2 minutes. 2 minutes of thought. The idea is going to be precisely what I said before. I think that also works, right? We're just gonna, like, every time we resolve an error, or like we solve an error, we make the current node sort of pose as the newly inserted node and make our parent be the current node. We rerun this until we reach the root. Right? So what we are going to do is we're going to implement something like while, right? While the current thing we have is let me think. How would we do this? While the current thing we have, yeah, is sort of different from null pointer. So null pointer will be, so think of current as the node to which the new node was inserted, right? So if I were to insert a new node, D would be current, and new node would be the child that would be right here, right? So just think of them that way. And so while current is different from null pointer, why? Because here we're going to start maybe on an insertion, we're going to start here, right? And then there's going to be a child here. Then once we resolve that error, we simply move up. So now current is going to be this guy, and we're going to suppose or think or make it seem like D was the newly inserted child, or like we're going to make B think that D was just newly inserted. So B will check whether all the conditions suffice and we'll try to solve them. After that, current will move to A, and so A will now believe, or we're going to make A think that B was newly inserted, and A is going to try and fix all the problems that that insertion sort of entails. And then after that, current is going to move up A, which is a null pointer because A has no parent, and only then will we know that we have solved all of the issues because we reached just the literal top of the tree. So while current is different from null pointer, what we want to do is we want to check these cases, right? So case 3 and all of that. There we go. Case 3. Case 1. I don't know why it does that. There we go. Some indentation. Great. So now, here, right? So current, think of it as like the parent, new node as the newly inserted child. And what's going to happen is it's going to try and check all of these cases, which is awesome. If we reach the root, then we would have been finished either way. This is bad. Okay, actually, okay. So this case is waiting for the newly inserted node to be the root. That means that current would be null pointer in that case. but that means that it wouldn't have entered this loop in the first place. So I think we're just gonna apply a while true, and eventually we know that this case will take place, and then we're gonna return out of that case, and then everything is gonna be sunshine and rainbows. Although I don't know, this is really sketchy. Fix this BS. we need to come back to this eventually, because this does not look good, but it's okay. For now, we will breathe in and breathe out, and like hope everything is fine. So case 0 is fine. Case 1, case 2, everything, right? All of this happens, and after all of it happens, wait. So case 0 is allowed to return. Case 1, where the unclosed red, is not allowed to return because we need to move up the tree, right? So there's that. Sort of to do, we need to move up the tree. Same thing here. If it's a triangle, we need to check that stuff has not changed. Move up the tree. And uncle is black, and new node forms a line with its grandpa. Sure. Okay. This is the case, the line case, and we don't return from it. Right. So here we need to also move up the tree. And let's see. This assertion no longer applies because, you know, we now are not returning from here. Yeah, so if line there, I just want to indent them to the same level, sort of like so that it just looks uniform and it's easier to parse through the code. Great. So if this is actually a line, then we need to go through this case. Great. Okay. So when we mean move up the tree, what we mean is think like now I can delete. Well, actually no. Move up the tree. Okay, what does that entail? That entails, say in case 1, that means that what we're going to make the next node believe is the new node is the current node. And the current node is going to become the parent of the current node. So we're moving up the tree, right? For case 1, this suffices. This is good enough. Why? Because case 1 only recolors. Problem though. Case 2 and case 3 perform a rotation, which means that the parent changes. So the parent we saw on our way down is different from the current parent. Is that something we care about? Great question. Is that something? Okay, let's see case 2. So in case 2, we see that the problem gets introduced again, but now as a sibling, right? It rotates it, and then here we are, right? So we would need to fix that problem. And it does not involve the parent, actually, because the parent is A, right, currently. it involves us, Z. Because Z's parent is now B, but B has no conflicts at all. The one with the conflicts is Z. So now to move up the tree, we have to consider which case we are in. Yeah, guys, I don't know what to tell you. This is yeah. Okay, so move up the tree. I'm just gonna sort of duplicate the code, and then we're gonna clean it up once we're done. We know that we can move up the tree in this way. When it's case 1, where we only read caller, we just make the new node equal to the current one, the current one equal to the current parent, and that's it. And then we continue, right? For the next case, which is case 2, we know that the new node is not going to be my current node, but it is instead going to be, yeah, it now depends on which rotation we've gone for. So if it's a left rotation, then it's going to be my left child. Sorry. If it's a left rotation, then it's going to be my left child, and if it's a right rotation, then it's going to be my right child, the one that introduces the problem. So here, right, we see that the problem is this one, so we rotate right. And when we rotate right, the problem is now in my right child. So that's what we need to keep in mind. So if the problem is originally, right, in the left child, sorry, if we left rotate, let's do the right rotation because that's exactly what's on screen. That example involves a right rotation, so else right rotate. So if we right rotate, we want to consider the current guy to still be the current guy. So that one we don't change. And we make it seem like the new node is actually my right child. Right? Just with like the example with A and Z sort of suffices, right? The current one, well, not so fast. No, yeah. We would need to swap these two variables. It will have to be the current one swaps places with the new node. Yeah. That seems more reasonable. What is going on with std swap? Hello? Yeah. Okay, perfect. So we swap those two, and yeah, they exchange sort of places. That's good. In the case of a left rotate, this is exactly the same thing. So then now we don't really need to worry about discriminating by cases. Great. So now we swap them, and then we continue. Awesome. Move up the tree. And here we also move up the tree. If the uncle is black and the new node forms a line with its grandpa, then we do something completely different, which is this stuff right here, where allegedly we solve any problem we could have, right? And so if we are to follow our reasoning from before, we would return here. Or, well, rather than return, well, yeah, return break, whichever one. And then it should work after that's done, right? I know I said I wasn't going to perform these early optimization because it could introduce a lot of bugs. But given the current situation, I think we may just follow our reasoning from before. And while we're testing this, if we ever encounter an error, then we revisit it. But for now, we simply hope for the best. I think that's what we're gonna do. We're just gonna hope for the best. We've been looking at redback trees for almost 4 hours and a half. So let's just throw a Hail Mary and believe this time. So once all of this is done, once the swallow tree completes, we are completely done with everything. So that seems great. I prefer break just in case we ever decide to include something after a while. And awesome, we have our insert in place. So yeah, I mean, I don't know what else to tell you. So these are tests. We tested left rotation. We tested right rotation. And now, error while processing. Expected semicolon on line 211. Hello? Oh, question mark. Hey, this is something, the C++ extension in VS Code is not really good. This should have been highlighted. The problem is that, the moment you introduce a template, this guy just, it's completely goes away. Oof. Why is the stream so laggy? Oh, it fixed itself. Yay. Wait, did it fix itself? Okay, yeah. Yoo-hoo! All right. I will assume insert is finished, and we will check how valid that assessment is by simply writing a test. We will write some tests, test insertion. As I mentioned before, testing is one of the things I hate the most. But in this case, I think it is much needed. we definitely need testing in this scenario. So yeah, I think I'm gonna let's add to here. Let's add a default template value for this guy, making it std-less. So then now we only have to specify int. Great. That's an arbitrary. Good. And so what we want to do is we want to, let's see, arbitrary that insert. I want to insert a value. Let's insert let's do it with the letters that we have in place. So I think string could okay, we need to include the string class. Sure. Include string. And we're going to test this with string, or actually, no. Why am I including string? I can just use chars. So let's just make it equal to char. Great. Or a car or something like that. Insertions. So let's move to the examples. And with the example, we are going to, it's going to be the final exam. If our insertion passes the test case of the example test case, then then we know we have reached the worry. Let's see. So if we insert 15, oh, error while processing. Whoa, what happened? What? See, like, the C++ extension didn't warn me about these errors before. Let me try and correct them real fast. Line 44, no matching construction. Retrieve.h 60, line 44 here. New node, val color red. Oh, I included the color. Okay. Let me just do it. Actually, no, I think this convention is fine. And then let me just change them. Val and then color red over here. Good. And then now, line 64. 64. It's a break. What are we talking about? Oh, line 217. No member named color in char. Line 217. 217. Here, node equals null pointer. And black, the node color. Oh, because it's an underscore. Instantiation of function template specialization requested here on line 49. Non-const L value reference to type color can bind. Yeah. Okay, this is what I was fearing would happen. We're just gonna play dangerous and say that this is the case, and then we're just gonna put black. So the reason why we do this is because when I apply color, I want color to be sort of the universal accessor for the color of a node because of the nil nodes, right? Calling the color member variable in a null pointer just gives you a null pointer dereference, which means that we'll be better off if we have a color function that whenever it detects a nil, it just returns black. The problem is that if we mix the two things, like you can obtain the color by calling the color function or by calling the color member variable, then it's going to be very confusing to explore the code base. So I want color to return a reference so that, you know, us as programmers can simply write this, like color equals this. The problem with that is that we are going to have a sort of like a problem with references, because if we return a value, an R value as a reference, like it makes absolutely no sense. So I think I'm gonna just be a little bit hacky with it. And yeah. Let's see, non-const reference cannot bind to bit field. Really? Ooh. Okay, I think the code is just falling apart. Let's look this up. I didn't know about this error. You cannot bind it to a bit field? You cannot bind a non-const L value reference to a bit field because bit fields do not have unique byte-aligned to memory addresses. Oh no. Well, this... yeah, we're kind of screwed. Ooh, okay. So that means we just cannot modify the bit field. I mean, I guess that's fine. I really wanted to access for the code to be like a little bit prettier if we had it this way. but I guess it's not gonna be possible. So we're gonna have to return only this, and then we can return our color black over here. With black. And then after this, we're gonna have to change the uses of color as a setter, which 31 mentions of color. Oh, okay. That was okay. So we use it basically everywhere. Yeah, how can I? I guess it's fine. I guess we'll just opt for the underscored color. It has an underscore just to like warn us, like, you know, be careful when you access this guy, because you know we don't want to try and get the color of a nil node. Grandpa definitely has a color. It should be fine. Then, okay, if uncle has red color, it means it's not a nil node, so we are also fine with changing its color. And color of the new parent equals this. Well, we replace it with that. Okay. And so other mentions of color appear here, where we need to change grandpa's color to something else. And then ooh, what is this? No. Okay. The color of the parent is gonna be black. Okay. I think that changes everything. Yeah, okay. Seems fine. It is tiring though. It is tiring. I know. Oh, it seems like we solved all the errors. That's great. So RB3, we're gonna insert 15. Let's now continue with the example. Whoa, what? Oh, yeah, this is the one I want. So 15, then it's supposed to be colored to black. And okay, we're gonna have to check their colors too. So in our RB3 to vector, I think we're gonna have to make it so that struct. Actually, no, I think I can just return. Okay, I want vector to be a thing that stores nodes, so that I can just take a look at it, and then instead of pushing the data, push the vector itself. Sorry, the node itself. And the node itself would just be sort of pointers. And yeah, this seems fine. Now we need to modify our previous tests to account for this. In the case of a left rotation, the RB tree to vector, I have a vector tree, but the vector tree needs to be a collection of integer nodes that have pointers. That should fix the call. No? Oh, yeah. Great. And so now the only thing we need to do is we need to say, well, for for every single int expected inside of expected, I need to assert that the vector tree size is the same as the expected size. And not only that, but we also need to make it so that the vector tree assert input size and plus I assert that they are equal in every position. So vector tree at I and then so the data equals expected at I, because we don't really care about the color. Good. Expected an impression. Great. And I think we're just gonna have to do the same thing down here. Below, restore a node t pointer with pointer. Great. And then here, instead of this, we have this. This is not a t, this is an integer. Great. All right. So I think we have modified everything to the point that, yeah, this is perfect. So to test insertion, now we can make expected be actually a no t. I think I'm gonna change things a little. No data, and then in here instead of pointers, I wanted to store the actual thing. Sorry, here, and then dereference that. Great. So that should fix all our problems. C++ extension. Hello. Okay. So what we're gonna do is we're gonna have an expected vector, and this vector will just simply store the nodes of what we expect to see in the tree. For example, what I expect to see is a black node that has its value 15, right? And then after that, what we're gonna do is we're gonna say, well, in the I is 0, and then we're gonna go through the expected of size, and then plus I on that. We're gonna assert, or sort of, I think that for the sake of the insertion, it would be cool if we could have bool arbitrary vector equal. And then we're simply going to accept two vectors of node ints. So arbitrary 1, and then we're just going to have arbitrary 2. And then here, we're just going to do exactly what we're planning on doing. We assert that their sizes are the same. Arbitrary 2.size. Sizes are the same. And not only that, but we also need to check that every single position, smaller than expected size, that every single position is the same. And by the same, we mean in the tree number 1, the ith position, the data has to be equal to tree number 2's position, data. And we also need to make sure that their colors are the same. Arbitrary1 at I.color is equal to arbitrary2 I.color. Great. And after that, we return true. Right? True. Or, well, I guess if this doesn't happen, then we return false. And then same thing. If this doesn't happen, then we return false. And I feel that's it. Almost. Question mark? Class. Oh my god. Class. No member named color in node. What do you mean? Oh, yeah. Because we need to access it through. Yeah. Color. And then color. Great. So now the only thing we need to do is we expect to see this, and then we simply assert that that is indeed the case. So assert that, what? No instance of function for call to color. Okay. I'll pass you the pointer to it, and will they be happy after this? Arbitrary 2. 1. Yes, perfect. So now we need to assert that the arbitrary vectors are equal. Who? Well, arbitrary 2 vector of our arbitrary and the expected vector. That should be enough. Yay. Oh. What was provided? Oh, yeah, sure. S3 vector node int like actual. And I can call arbitrary to vector of the arbitrary and then pass in actual. And this arbitrary must be a pointer. And then we can call actual. Let's wait. Great. What? This is strange. So it's telling me that arbitrary2 vector is a node T. Oh, I see. I mean, you can just simply call this with the head or the root. Arbitrary.root. That should be it. Please. Oh no, C++, please. Let us go. Deduce conflicting types. Oh yeah, no, this is supposed to be an integer arbitrary instead of a char tree. And please tell me that's everything. Yay! Oh my god. Oh my god, that was such a pain. Okay, let's go. So now, sorry if I seem a little bit like not as energetic as usual. It's just that it's draining me. Like this problem is, you know. So what we expect to see is a black root, right? Black 15. Let's yeah, I think we can just abstract this away too. Yeah, arbitrary equal to vector, and then we can just accept, rather than this, we can accept an arbitrary of some type t, template this away, type name t, and then type name comp, then we pass this comp, and this guy will be, we'll assume it's etherealist t. Where we accept that arbitrary, and then we have a vector node, which is going to be the vector. Arbitrary. Vector node is going to be the vector. I want to pass that one by value, but this one by reference. Or actually pass me a pointer to your arbitrary, and I'll be happy. And what we are going to do is we want to create inside of here this actual one. So actual one. And arbitrary one will just be actual. And arbitrary 2 is just vec. So that way we can simply assert arbitrary equal to the vector equal to the vector, well, actual, no, we simply pass the arbitrary as a pointer, and then the expected one, which we can actually just write like this because we didn't pass it as reference. We don't really care about memory usage when it comes to tests. And this is a capital T. And this is supposed to be a pointer, so arrow. And is there anything else? Please C++. Let's see. Arbitrary. Oh, great. Awesome. Arbitrary equal vec. What is the problem now? Please. 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 Let's see. Oh, okay, I see. Should be a vector of objects like this. Let's wait for C++ to reload. Yay! Okay, perfect. We did. Oh my god. Okay, now it's gonna be like way easier, right? Because then after this is done, then we see how Michael inserts 5. And now we just need to include the pre-order traversal of this, of the tree, like the way we're expecting it to be, arbitrary. And then we're gonna have color to be, well, we know that the root should be black, should be 15. And we also know that the next node, I'm actually going to include them in a cascade a little. Yeah, like this. And then that the color is red and that it should be a 5. Awesome. What happens after? Let's see. After we insert 1, the final result should be 5 black. Okay, so we insert 1, and then the final result should be arbitrary equals to the vector of, we pass in our arbitrary, and then we pass what we expect. And what we expect is a black colored root. So that identified. And then according to pre-order traversal, we need a color red one. One. Great, awesome. And now what we need is a color red 15. Right? Good. That's all. And after that, okay. Yeah, certain board. Whoa, what did we do? Huh? How did we end up with this tree? Oh no, I think it, like the order of insertion and stuff, it's gonna change how the tree is laid out. So I cannot just start inserting elements and then it will end up like that. Okay, let's try it. Let's try this as sort of a basic one. Basic test. Oh no, we made some changes. Wait, what's the problem here? Candidate template ignored, could not match node type parameter 00 against node int star. What are we talking about? Oh, this should not be a pointer. And so this should be just a dot. And the same thing applies for you guys over here. Where is it? Where is the culprit? Here. Oh, I updated that one, but not the previous one. Okay. Let's see. Oh, awesome. All right, now we just need to call our test for the insertion. And we can execute it. Finally, so much time spent. Test arbitrary with debugging symbols and everything. Awesome, no problems at compile time. Now we just run it. No! We got a seg fault. We got a seg fault, guys. See, that's the reason why. Oh my god, somebody else followed. Yo, hi Goko00 if you're still watching. I'm so sorry the stream is not that entertaining right now. It's like we're currently going through segmentation fault hell. We're currently going through, like, we've been battling with red and black trees for what is now 5 hours. I don't even know what to say. That is my reaction. It's like, it's okay. It's okay, you know, it's like these things happen. But there's a reason why this channel is called SharifSegfaults, because I'm very prone to creating these errors, these segfaulting errors, and I think many people are too. It has to be the most common error in C++, which is why I like it as a name. But I hate it as an error. It's it's really bad. Well, okay. The only way we can deal with this is debugging. Let's debug. Where is the seg fault? Oh, what? So we're trying to call the uncle of someone that doesn't have an uncle. And this is really bad. So let's see. Where did we call uncle? Case 1, new node's uncle is red. Oh, okay. I see. So what's going on is if we have, say, we insert the root, so then that's the usual one. It's red, and then we color it black, and then it should be fine. And after that, we insert the next node, which is a red one, right? The one red. So then we insert it. And what ends up happening is that, yeah, because of this, right, we know there are no conflicts. But, oh no, never mind. We do account for that. What? Okay, let's run this again. Now with a breakpoint over here. So we val 5. What? Huh? The first insert should have triggered, no? Oh no, never mind. If the tree is empty. Yeah, okay, it went through here. Okay. Now we're trying to insert 5. And when we try to insert 5, we check whether or not the current has its color being black. And that should sort of immediately return. Oh. What? How did it not? The little color of current is black. What is going on? Did I mess up the color function? If node is a null pointer, return black. Otherwise, return the node's color. Huh? Current was black. Color of this... Yeah. What? Alright, run it again. Wait. Current is black. And if we step into this thing, we have that flush color is black. So no matter what happens, we return black. And then here, okay, if I call color of current, will it let me? Oh, it doesn't. That's fine. Color of current is equal to black, then return. So I assume we return, no? And we don't. But why? Let me see, can I just include this as a new line and then include like a little stop point before to know whether or not... Okay. Let me recompile. Okay. Reset, and then let's run it again. Yeah, guys, I mean, this is a very annoying part of the stream. So go out, drink a coffee, close the stream and come back later because we're going to be here for a while. And I've made it my goal that I'm going to finish at least the insertion for red black trees today. It cannot pass from today. Okay, that's a compromise, or like my compromise. So yeah, let's go with that. Color current, color black. Current is indeed black. Okay, so it did skip that. So now we are on a second call. My only problem is that val is exactly the same, but there's only one insert 5. But then val is the same thing. So there's something I'm just not understanding. Because it's skipping this thing. I don't know why. Why are you skipping the comparison? Let's see. We run this. Okay. This is our first skull to insert. And then this is the 15. Val is 15. And then we simply return. Great. Now we assert this, and then we insert 5. When we insert 5, we go here. No, the tree is not empty, so we skip. And then while true, we try to go down the tree. Currently, this should return. We should enter this if. This thing doesn't have a left, so then we link them together, and then we break out of the loop. Yes. Now, current has as color black. Yeah, black. So then it says, if color of current equals black. So we step into what color is doing. Right? Step into it. And we see that the node that's being passed is something that has as color black. So we say, okay, is node a null pointer? Well, clearly not, because it has information. And so we're going to go here, and then we're going to return node, and then it's color. But when we step over, right, and we go back here, the thing skips the return for absolutely no reason. Why? Why? Why is it skipping the return? Like, current is indeed black. No, like, am I just done? Like, color of current? It's a syntax error, but like, black. Yeah, I cannot add something to the watch list related to this color function. What is happening? Okay, let's try something new. Let's simply access the member variable directly and try and see what happens. Let's see. Okay, so we're at current, continue. This is 15, so this is fine. Then we try and insert 5. And with 5, something interesting happens. We enter the while true, we break out of the loop. Now we're at comparison point. Current color is black. And if we step over, it does some weird thing, and then it... What? And of course 5 is not going to have an uncle, because it's the literal child of the root. So why are we... If anyone in the chat can help with this, like, if you know the answer, that'd be great. But my hypothesis is that this has something to do with bit fields, and that C++ does some weird stuff where, like, if you compare a bit field to something else, it grabs the entire byte rather than only the one bit, and then it like messes everything up. See, I'm not sure. So we're gonna have to seek help from our mutual friend. Print. Like, we need to print stuff now. So cur color. Then we're gonna print a space, and we're gonna print the comparison between these two. Because red, okay, let's baptize red as 0 and black as 1. Just so that we know which one's which. And then let's compile this again. Oh, wait, sorry. Okay. Whoa, candidate function not known. And color to, okay, I'm just gonna convert this to an integer and call it a day. Okay. G++. What? How are so many errors introduced? I'm gonna wrap you into blanket and you true. Char, like, I don't know. Okay, great. And let's now run this. Well, the problem is that if it's a short, okay, how about a short? Will it accept a short? Thank you. All right, let's run this again. But now, actually, I just want to run the executable itself. Like this guy. Okay, -1 and 0. What is that supposed to mean? What? Huh? Like, how are we getting -1 in the color if they're red and black and they're both 0 or 1? Is it because of the bit field? Yeah, it has to be the bit field. It has to be the bit field. Okay, the bit field is introducing problems to us. So I think we're gonna have to look for a solution. So I'm not too familiar, like, I've been using bit fields, yes, but I've never really encountered a situation like this where the comparison doesn't work. Maybe it's because of the fact that we're using it as an enum. Using bit field as enum C++. Is it safe to use? Okay. This explains a lot. A lot. Yeah, I should have paid attention to this. Okay, so now we need to specify that what we need is, okay, I see. Wow. You know, learn something new every day. So I see. Okay. So we're supposed to store stuff. Okay. Perfect, perfect. Now this makes total sense. Let's try and recompile again. This is this is basically Sisyphus. Like we're just trying and trying and trying and oh my god, it worked. Wait, did it work? Yeah. Oh, okay, this is great. This is great. Okay, at least it worked. Awesome. This is great. Let's see. Okay, now that we have this working, let's take it's already 7:22 where I am, PST time. So it's already been 5 hours of stream. Let's pause for like 5 minutes. Okay. So I'm gonna be back at 7:27. Okay. And once I'm back, we will continue. Perfect. All right. Bye bye. Well, not bye bye, right? The stream is gonna continue, but we're going to simply. I'm just. By the way, to those of us who were in the previous stream, notice that like I worked so much on the OBS on trying to make it pretty and like very accessible to you guys. So now, actually, now that I'm thinking about it, I may end the stream and resume at probably 8:30 my time. So let's take an hour break because I need to do some other stuff. I need to eat. All of that. Coding is very addictive, so we often forget about those things. And yeah, and then I'll see you guys again at 8:30, 8:30 my time. So basically 30 minutes from now. Okay, for me it's well, actually, sorry, an hour and 7 minutes from now. Perfect. Okay, and as I was saying, I've been like working with the OBS since yesterday, and look, now I can like switch scenes. I have like this one, which is like just us, right? It's like me and then like you guys here in the, I don't know where to point, here in the chat, and then the coding scene also has the chat here on the like upper part, right? Like over here. It's just that the messages fade after 30 seconds have passed. And I also have this screen that is the starting soon screen. Ooh. Okay. All right. I'm gonna stop joking around. And as I mentioned, we will be back at 8:30. So in an hour and 6 minutes from now. Okay. I'm gonna leave you with the beautiful starting soon screen. Bye bye.